Hello everyone, good evening. Good evening guys. Good evening, good evening, good evening. ऑडियो वीडियो क्लियर है भाई? बताएं। एंड आपको हिंदी में पढ़ना है कि इंग्लिश में पढ़ना है, बोलिए भाई। बिकॉज यहाँ पे बहुत सारे स्टूडेंट ऐसे हैं जो इंग्लिश में कंफर्टेबल हैं, बहुत सारे स्टूडेंट ऐसे हैं जो हिंदी में समझ सकते हैं और इंग्लिश में भी समझ सकते हैं, तो वो लोग इंग्लिश की तरफ ही मुझे बहुत बताइएगा। बोलिए भाई। ऑडियो वीडियो क्लियर? बहुत सारे स्टूडेंट ऐसे हैं जो मेरी तरफ से क्लियर है भाई। ऑडियो वीडियो बताएं सब लोग। ऑडियो वीडियो क्लियर है? Your wish, okay. Then better we should continue in English, because ultimately the batch we are going to start is also in English. Okay, so okay, Dax, thank you. So today's session is about power electronics. Okay, we'll discuss previous year questions of power electronics. We'll start from inverter. Okay, and then we'll go backward because the main जो the most important topics हैं, there are inverters and DC-DC converters. These two topics are very important, and in entire power electronics, let's say if 5 to 7 questions are there in the exam, then out of those 5 to 7 questions, at least 3 to 4 questions will be from these two chapters. So in today's session I'll try to cover inverter and DC-DC converter part. Okay, so let's wait for 1 or 2 minutes and then we'll start. Till then, if you want to ask me something, you can comment your doubt in the comment section. Okay, you can ask your doubt in the doubt section. I'll reply. Okay, so guys, I think we should start now. So tell me, all these questions are visible or not? I think I can zoom this and then move it like this. Okay, so let's first start with these two questions. Question number 27 and 28. These are asked in 2017, and this question is again to 2017. Okay, so there are two questions. First, let's target these two questions. Okay, will you solve it for me or should I solve it for you? Look, the first question is question number 27, and it says that a three-phase voltage source inverter with an ideal device is operating at 180-degree conduction mode, okay, is feeding a balanced star connected resistive load. The DC voltage input is VDC the peak of the fundamental component of the phase voltage. Okay, so how to solve this problem? It's a very simple switching problem. Okay, if you know the basic transient theory in network system, then you can easily solve this problem. Okay, so will you try it for 2-3 minutes, or should I solve it for you? It's a 1-mark question. No need to remember any formula, just apply the concept. Okay, okay guys, let's try to solve it. So we have a 3-phase voltage source inverter. So if you look at the diagram of 3-phase voltage source inverter, it will be like this. We have 3 legs, leg A, leg B, and leg C. It's always a better habit to draw the diagram first, because when you see the diagram, 50% of the problem is already almost solved. Okay, so this is the VDC voltage, and we have leg A, leg B, leg C. So I have taken the output from this leg A, and then leg B, and then leg C. And the load is star connected resistive load. So we have star connected resistive load. Let's say the load is like this, and the load is balanced. Okay, the load is balanced, so it is connected like this. We have star connected balanced load. Okay, input DC voltage is VDC. The peak value of the fundamental component of the phase voltage, whatever be the phase voltage, we need to calculate that voltage. Okay, so how to calculate? What I can do is, I can connect 2 capacitors here, okay, and make this point as a reference ground. Okay, since these 2 capacitors are of equal value, so you can say that this VDC will divide equally across them. Okay, wait, I think my image is disturbing this. Okay, just give me 1 minute. Okay, let me move this. I can move it here. Now I think it will not create any issue. Okay, now it's visible. Okay guys, so we have this 3-phase voltage source inverter. I have connected these 2 capacitors C and C, and we know that this VDC will divide equally across them. This is VDC by 2, and this is also VDC by 2. So with respect to ground, this voltage will be VDC by 2, and this voltage will be minus VDC by 2. Okay, this is leg A, this point is B, and this point is C. Okay, so if this point is A, this point will also be A, this point will be B, and this point will be C. Now, and let's call this point as O. So let's find this voltage with respect to this O point. With respect to this O point, what is the voltage of A? So I can draw it, voltage of A with respect to O. Okay, now you can clearly see that the conduction mode is 180 degree. It means out of that complete cycle, 50% of the time is this switch is closed, and 50% of the time this switch is closed. When this switch is closed, the upper switch is closed, the point A voltage will be plus VDC by 2, because this level will come here. Okay, and when the lower switch is on, minus VDC will come here. So you can say that VAO will be like this. It will be a square wave. It will be a square wave. This level will be VDC by 2, and this level will be minus VDC by 2. Okay, this is pi radian, and this is 2 pi radian. Okay, I hope you understood it. This is VAO, voltage of this point A with respect to O. Similarly, we can calculate VBO. Just delay this wave by 120 degree, and VCO will be the same wave shape. We have to just advance the wave by 120 degree. So we can easily calculate VAO, VBO, VCO, but the required voltage is this voltage, phase voltage. This voltage is required. Now how to calculate this voltage? To calculate this voltage, what I need to do is, I have to look at this voltage first. I have to look at this voltage. Whatever this voltage is, so VAO minus, let's call it N, neutral point voltage, okay? So whatever the voltage at this level A minus the voltage at this N level, then that voltage will be the phase voltage across this resistor R, okay? I hope you understood it. Moreover, there is one more point. The fundamental component is asked. In the problem, the fundamental component is asked. At this point, we know that we have this voltage. Similarly, at this point and this point, we know the voltage wave shape. When you look at the fundamental component of this voltage with respect to ground, then the fundamental component will be like this. Okay, the fundamental component at this point with respect to ground will be like this, and the value will be the peak value will be 4 into VDC by 2 divided by pi. This will be the peak value of the fundamental component of this voltage. It comes out to be 2 VDC by pi. Okay, this is the fundamental peak value of this voltage. Now, as far as fundamental is concerned, the voltage at this point will be 0 volt for fundamental component. Okay, for fundamental component, the fundamental component at this point is of this peak value. I mean, if you write VAO 1, then this value will be 2 VM by pi, 2 VDC by pi, 2 VDC by pi sine of omega naught t. That will be the fundamental component at this point with respect to ground. Similarly, you can write VBO1, and that will be 2 VDC upon pi sine of omega naught t minus 120 degree. Okay. Similarly, VCO1 we can calculate 2 VDC by pi sine of omega naught t plus 120 degree. Okay. So this way we can write fundamental component of this voltage, and this voltage. And we know that for fundamental component, if you calculate the voltage of this neutral point with the help of nodal, it will become 0. Okay. You can easily check that. So you can say that this neutral point is grounded as far as fundamental is concerned. Okay, it is not grounded for triplet harmonic. Remember, for the neutral voltage is not 0, but for fundamental component this voltage is 0. Okay, you can say for fundamental component this voltage is this point is grounded as far as fundamental is concerned, because at these point we have balanced voltages. So if across a star, if you look at the star connected load, in a star connected load, if these voltages are balanced, then and of fundamental frequency, then this neutral point will always be at 0 volt, whether you connect it with the ground or not. Okay, but remember, the neutral voltage will never be 0. The overall neutral voltage will never be 0. Only the fundamental component or the third harmonic component or fifth harmonic not third harmonic, triplet component will be present here. Okay, it means this point will not be actually grounded for triplet harmonic. I mean, if you want to calculate Vn, then you will get triplet harmonic voltages. Okay, you will get triplet harmonic voltages. Give me 1 minute. So I was telling that as far as fundamental is concerned, this neutral point has to be at 0 volt. For fifth harmonic, this will again be 0 volt. But if you look at the triplet harmonic, 3, 9, 15, odd multiple of 3. Okay, if you look at the triplet harmonic component at this point, the same voltage will available here. Okay, remember that. So the overall Vn will not be 0. But as far as fundamental component is concerned, this voltage will be 0. It means as far as fundamental is concerned, you can just ground it. and this point voltage has the fundamental component of this. So what will be the phase voltage? This voltage itself will be the phase voltage. Okay, this is the fundamental component of the phase voltage, because this voltage is measured with respect to ground, and this point is also grounded as far as fundamental is concerned. So you can say that this voltage difference will be equal to VAO itself for fundamental component. Okay, so you can calculate this phase voltage, and the peak value will be 2 VDC upon pi. So the answer is Bombay, 2 VDC upon pi. It was a simple problem and you can easily solve it. Okay, now let's say in the same question, if they ask the neutral voltage, what will be the RMS value of the neutral voltage? In the same problem, let's say they ask what will be the RMS value of the neutral voltage, VN, RMS value of VN. Let's say they ask this value, then how to solve it? VN will never be 0. It is not actually grounded. We have grounded it for the fundamental component, but actually VN is not 0 volt. VN has triplen component, triplen harmonic component. How to calculate those triplen harmonic component? How to draw the wave shape of VN? How to draw the wave shape of VN? How to draw it? So for that you have to apply the nodal method to calculate this VN, and I hope you will do it for yourself. But again, that will be the very good question, so you have to solve it. But for this question I have solved it for you. Okay, let's come to the next question, guys. The next question on your screen is, if you look at question number 28, the figure below shows a half bridge voltage source. So the figure is already given. It is a half bridge voltage source inverter supplying RL load. R is 40 ohm. R is 40 ohm. L is 0.3 divided by pi Henry. Okay. The desired fundamental frequency is 50 Hertz. The switch control signal of the converter are generated using sinusoidal pulse width modulation. Okay, with modulation index 0.6. At 50 Hertz, the RL load, the active power of 1.44 kilowatt. The active power absorbed by this load is 1.44 kilowatt. The value of the DC source, VDC, we need to find. Okay. Now, if you look at the output voltage, let's say this is the polarity of output voltage. Now, what will be the wave shape of this output voltage? Let's draw the wave shape of output voltage. For that I need to rub this. Okay, let me rub this. Okay, now let's calculate the wave shape of output voltage, V out. Okay, you can see that when S1 is closed, V output is VDC, and when S2 let's call it S2, when S2 is closed, the output will be of opposite polarity. It will be again VDC, because this voltage source will connect across the load. But since the polarity is opposite, the negative side will come on this side and positive side will come on this side. So you can say that when S2 is closed, output voltage will be minus VDC. When S1 is closed, output voltage will be plus VDC. Okay. When S2 is closed, minus VDC. So this will be the wave shape of the output voltage. Okay, I hope you understood it. Now the fundamental component of this voltage, what will be the fundamental component of this voltage across this load? Since we use PWM, sinusoidal PWM, so what you can do is you can just multiply this amplitude VDC into with modulation index. So the output fundamental component has the peak value of VDC into 0.6 VDC. Okay, this is the peak value of the fundamental component of the output voltage. Okay, it is given that the load will absorb this much of active power only because of fundamental component. Okay, and we need to calculate VDC. Now this voltage 0.6 VDC, this is the peak value of the fundamental component. What will be the current? The current will be this peak value 0.6 VDC divided by the magnitude of this, and the magnitude of impedance is 40 plus J 100 pi. Omega is 100 pi. Fundamental frequency is 100 pi radian. 100 pi into 0.3 by pi. Okay, so it will become J30. and if you take the magnitude of that, it will become 50. So this is the peak value of the fundamental component of the current. It comes out to be 6/500 VDC. Okay, so this is the peak value of the fundamental component of the current. Now what will be the RMS current? RMS current will be 6/500 VDC by √2. This is the RMS value of the current which will flow, RMS value of the fundamental current which will flow through it. Okay, now if you want to calculate the active power, then take the square of this RMS component of the current into 40. Okay, and this must be equal to 1440 watt. Okay, IRMS square into R. This is the active power, no? So this is the IRMS square into R, and it comes out to be 1440. Now from here you can calculate VDC. Okay, cancel this, take this 4 on this side. Okay, so and then take the root. So if you take the root, then it will become 6/500 √2 VDC, and it will be 12/2 if you take the root of that, na? So 12/2 is 6, so it will be 6. 6 is cancelled, so VDC will be 500 √2. 500 √2. Answer is Calcutta. Okay, so this was again easy peasy problem. Nothing to worry. Let's move to the next question. Let's move to the next question, guys. And the next question on your screen is question number 29. Okay. Now question number 29. I think you can solve it for at least spend some 2-3 minutes on this question. Okay. Let's see the question. Question says the output voltage of a single phase full bridge voltage source inverter. Since the diagram is not given, so it's good to draw the diagram. Okay. Output voltage of a single phase full bridge voltage source inverter. So single phase full bridge voltage source inverter will be like this. It is a single phase full bridge voltage source inverter. Okay, and this is VDC. The output of a single phase full bridge voltage source inverter is controlled by unipolar PWM with 1 pulse per half cycle. Okay, the fundamental RMS component of the output voltage is to be 75% of the DC voltage. Whatever DC voltage we have applied here, the fundamental component of the output voltage, let's say this is the output voltage. So the fundamental component of the output voltage is 75% of DC voltage. It is given. The fundamental RMS component, obviously RMS component, this is the RMS value of the fundamental component. The fundamental RMS component of the output voltage is 75% of the DC voltage. The required pulse width in degrees. We need to find the required pulse width. Okay, and it is controlled by unipolar PWM. Okay, unipolar PWM means the voltage will be like this. Okay, this type of output voltage will be there. 0 pi. It means from 0 to pi you have a width like this, and then pi to 2 pi you have the width like this. Okay, the output voltage of single phase full voltage are controlled by unipolar PWM with 1 pulse per half cycle. You can see that 1 pulse per half cycle. This is the half cycle, so we have 1 pulse per half cycle. Let's say the width of this is D. Width is D. It is given that the RMS value of the fundamental component of this voltage is 0.75 VDC. We need to calculate this D in radian. In radian, what will be the D, or in degrees? Okay, let's first find the D in radian and then we'll convert it into degrees. Okay, so how to calculate that? It's very easy. What you can do is, let's first calculate the fundamental component of the fundamental peak value. Okay, how to calculate the fundamental peak value? What you can do is you can apply the quarter wave symmetry, because this wave contain quarter half wave symmetry. Okay, a quarter wave symmetry. So if you know if you have the understanding of quarter wave symmetry, then you can say that this is pi by 2. This is 1/4 period. Okay. This is d. So this point will be pi by 2 minus d by 2. Okay. Because this entire length is d, this half length is d by 2. So this point will be pi by 2 minus d by 2. I hope you understood it. Okay. So now let's calculate the peak value of the fundamental component. How to calculate that? You can apply the quarter wave symmetry. Since this function is odd, how I can say that this function is odd? If you repeat the wave on this side, you will get the wave like this. And you can see that there is odd nature of the function and it contains odd half wave symmetry. In overall, it will become quarter wave symmetric. So you can say that the fundamental peak value will be 4 by pi integration 0 to pi by 2 ft into sine of omega naught t d omega naught t. If you remember, this is the peak value of the fundamental component. I don't know how many of you know this quarter wave symmetry. I applied that symmetry. Since this ft function is actually the v naught t function, okay? So here I have to write v naught t. I have to write v naught t. Now, if you look at the v naught t, it does not start from 0. It starts from pi by 2 minus d by 2 and then up to pi by 2. Okay. So this integration I have to solve 4 by pi integration from pi minus d by 2 to pi by 2. Pi minus d by 2 to pi by 2, and this v naught t is d sine of omega naught t d omega naught t. If you solve it, it will become 4d divided by pi. Integration of sine is minus cos. Upper limit minus lower limit, it will become cos of pi minus d by 2. Okay. So this is the peak value of the fundamental component. If you divide it with root 2, it will become RMS value of the fundamental component. And this has to be equal to output voltage is VDC. VDC. Okay. This is 4 times of VDC. Okay. 4 times of VDC by pi. And then you have to take the RMS. For RMS, you have to divide it with root 2. So this is the peak value of the fundamental this is the RMS value of the fundamental component, and it has to be 0.75 VDC. Then VDC will cancel. Okay. From here, cos of pi minus d by 2 is equal to 0.75 pi root 2 divided by 4. Okay. From here we can calculate the value of d, but that d will be in radian. Okay, let me solve it for you. So it will become 0.75 into pi root 2 divided by 4. Okay, so this comes out to be 0.83. If you take cos inverse of that, then you will get 33 point. Now pi minus d by 2 is equal to 33.58 degrees. Okay, 587 degrees. Pi is 180 degree. Okay, so if you take this 2 on this side, then it will be 67 point something, and then 180 minus. So in degrees, d has to be 112.82 degree. Okay, so this is the correct answer. I mean, for this pi you have to replace it with 180 degree because we need the d in degrees now, and this side is also in degrees. So what you can do is you can replace this pi with 180 and then you can calculate the value of d. It comes out to be 112.8. So again, this was a simple question. Let's move to the next question, guys. Let's move to the next question. The only thing is the basic understanding of the concept. Okay, so next question is question number 30. Now let's read the statement. A single phase inverter is fed from a 100-volt source. So we have a single phase inverter. It is fed from a 100-volt source and is controlled using a quasi square wave modulation scheme produced by the output voltage as shown in the figure. So this is the output voltage of a single phase voltage source inverter. Okay, it is provided to us. The angle sigma is adjusted to eliminate the third harmonic. Okay, angle sigma is adjusted such that the third harmonic component of the output voltage becomes 0. Okay, perfect. Under this condition, for Vt, the magnitude of fifth harmonic component as a percentage of magnitude of fundamental component, we need to calculate the amplitude of fifth harmonic component as the percentage of fundamental component. Means, let's say fundamental component is of 100 volt and fifth harmonic component is of 30 volt. Then the percentage of fifth harmonic is 30% of the fundamental. Okay, so that way we have to calculate the magnitude of fifth harmonic component as a percentage of the magnitude of the fundamental component. Now how to do that? First of all, calculate this sigma. How to calculate sigma? Make the third harmonic component 0. Okay, from there you can calculate sigma. How to calculate the third harmonic component? We can calculate the peak value of the third harmonic component with the help of quarter wave symmetry, because we know that this function is odd. How we know that? Because if you extend this function in the negative direction, this is sigma, this will also be sigma, and then it will be like this. It will be like this. So it's an odd function, you can clearly see. It is an odd function and it has odd half wave symmetry. So all in all, it has quarter wave symmetry. With the help of quarter wave symmetry, we can calculate the amplitude of the peak value of the third harmonic component and make it equal to 0. Let's calculate the amplitude of third harmonic component. So 4 by pi integration 0 to pi by 2 V0t sine of 3 omega naught t d omega naught t. This is the peak value of the third harmonic component of the output voltage. We know that from 0 to pi by 2, V0t is not present. V0t is present from sigma to pi by 2. So what you can do is, you can write it like this: 4 by pi from sigma to pi by 2, and V0t is 100 volt, 100 sine of 3 omega naught t d omega naught t. Okay. Now if you calculate this, it will become 400 by pi, integration sign is minus cos 3 omega naught t divided by 3. Okay, and put the limit from sigma to pi by 2. Okay, in this you have to put the limit. So 400 upon 3 pi into upper limit, it will become 0, lower limit is cos of 3 sigma. Okay, upper limit minus lower limit I have done, and this has to be 0. This will be 0 only if this 3 sigma will become 90 degree. It means the sigma has to be 30 degrees. The value of the sigma has to be 30 degrees. Once we calculate this sigma, now we can calculate the amplitude of fifth harmonic and the fundamental. How to calculate? Let's say the amplitude of the fundamental, and that will be from sigma to pi by 2. Sigma is pi by 6, 30 degree, na? 30 means pi by 6. Okay, so it is pi by 6. From pi by 6 to pi by 2, ft is 100. Since we are calculating the peak value of the fundamental component, so sine of omega naught t d omega naught t. Okay, this is the way we have to solve it. So it will become 400 by pi, integration of sine is minus cos, upper limit minus lower limit. So upper limit is 0 and lower limit will become cos of pi by 6. Okay, so this is the peak value of the fundamental. Now what about the peak value of the fifth harmonic? 4 by pi integration from pi by 6 to pi by 2 ft sine of 5 omega naught t d omega naught t. Okay, and if you calculate this, it will become 400 by pi, integration of sine of 5 omega naught t is 5 and minus cos of 5 omega naught t. Okay, and the limit, lower limit is pi by 6 and the upper limit is pi by 2. So if you solve it, the peak value of the fifth harmonic component is 400 upon 5 pi, upper limit is 0, lower limit is cos of 5 pi by 6. Okay, so this is the output voltage, peak value of the fifth harmonic voltage, and this is the peak value of the fundamental voltage. Now we have to find the ratio. So to find the ratio, what you can do is you can take this, divide by this and multiply by 100. Okay, so this divide by 400 by pi cos of pi by 6 multiply by 100. Now you can calculate. 400 by pi is cancelled, so it will become cos of 5 pi by 6 divided by 5 cos pi by 6 into 100. This much percentage of fifth harmonic is present with respect to fundamental. Okay, so I think this was again easy peasy problem, nothing to worry. Okay, so you can calculate like this. I mean, you have to apply these steps. Let's move to the next question, guys. And the next question on your screen is question number 31. And I want that you should spend some time on this. You have 2 minutes, okay? 2 to 3 minutes. 3 minutes I am providing, okay? Think about this question. First, let's read the problem. A single phase full bridge inverter fed from 325 DC produces a symmetric quasi square wave AB. So this is the square wave which is produced by, what happened? Wait. Okay, wait. Okay, now you can read it. Okay, so a single phase full bridge inverter fed by 325 volt DC produces symmetric quasi square wave across AB as shown. This is the output voltage. Okay, to achieve the modulation index 0.8, the angle theta is expressed in degrees should be. It is given that the modulation index has to be 0.8. We need to find this theta, okay, in degrees. Okay, and it is given that the modulation index is defined as the ratio of the peak of the fundamental component of VAB to the applied DC. Applied DC is 325, and the peak value of the fundamental we need to calculate. Okay, that ratio has to be 0.8. Now we need to find this value of theta. How to do that? Again, it's an easy problem, so spend some 2-3 minutes on it. Actually, by giving the definition of this modulation index, he has made the problem very simple. Okay, even if this statement was not mentioned, then also you have to do the same. Okay, so let's spend 2 to 3 minutes on this. So 3 minutes I am providing right now. It's 6:37, so up to 6:40 you have to solve it. Okay, try to solve this problem, guys. It's very easy peasy problem. Solve it. Do it, guys. You have 1 more minute. Time over. Time over. Let's see. So first we need to calculate the fundamental peak value. We know that this wave contains the quarter wave symmetry. This angle is theta and this is also theta. So if you look at the fundamental component, this will be the fundamental component. Okay, let's calculate the peak value. For calculating the peak value, we can apply the quarter wave symmetry. So 4 by pi, I mean there is no need to remember any formula. 0 to pi by 2, not 0, theta to pi by 2, theta to pi by 2, because the function is available only in this range. In 1/4 from theta to pi by 2 it is available. Okay, and the VDC is 325 sine of omega naught t d omega naught t. This is the peak value of the fundamental components. You can calculate that. So it will become 1300 divided by pi. I have taken this 325 out and multiply by 4. So it will become 1300 by pi. Integral of sine is minus cos omega naught t. Upper limit minus lower limit is cos theta. Okay. This is the peak value of the fundamental component. Right. Now, what will be the modulation index? This peak value of the fundamental voltage has to be equal to modulation index into 325. It is given, na? Modulation index is defined as the ratio of the peak of the fundamental of VAB to the applied DC. I mean the peak of the fundamental divided by applied DC. Applied DC I have taken on this side. Okay. So from here you can calculate the modulation index has to be 1300 cos theta divided by pi into 325, and it comes out to be 0.8 because modulation index is provided to us. Now you can see that 325 1300 divided by 325 is 4. So cos theta will be equal to 0.8 pi divided by 4. So cos theta will become 0.2 pi. Okay. From here you can calculate the value of theta. Okay. So it will become cos inverse of 0.2 into pi, and it comes out to be 51 degree. Theta equal to 51 degree. Okay. So again this problem was easy peasy, nothing to worry. Okay. So this was asked in GATE 2021 because I have the question up to GATE 2021. So I am solving the question previous to 2021. Okay. So I have solved 2021 problem and problem from 2021 and then 2020 and 2019, 2017, 2017. Okay, these problems I have solved. Now let's move to the next. So let me okay guys, now I have this problem, question number 21. Okay, now you should solve this problem. Okay, so let's see how many of you can solve it. Question number 21, let's first read it. Single phase full bridge voltage source inverter, input is VDC, it's a single phase full bridge voltage source inverter, has an output frequency of 50 Hertz. Okay, it uses unipolar pulse width modulation with switching frequency 50 kilohertz and modulation index of 0.7. For V in 100 volt, it is given as 100 volt. L is 9.55 millihenry. Okay, and C is 63.66 microfarad. Okay, R is of 5 ohm. The amplitude of the fundamental component of the output voltage V naught T. What will be the fundamental component of this output voltage? Okay, I want you to spend at least 3 to 4 minutes on this problem. Think about it. If you can't solve, nothing to worry, I'll solve it for you. But first understand the problem, read it carefully, understand it, and then we'll solve it. Okay, so I have given you 3 to 4 minutes to solve this problem. After 3 to 4 minutes I'll discuss. Okay, do it guys. It's 6:45. I'll discuss it at 6:49. Okay, after 4 minutes I will discuss this. Do it fast, everyone. Do it fast, everyone. Two more minutes. Do it, everyone. Do it fast. Okay, time over. Time over. Let's try to solve this problem. Single phase full bridge voltage source inverter is shown in the figure, has the output frequency of 50 Hertz. Okay. Output frequency of 50 Hertz. It uses unipolar. Oh, wait. Wait. So this is the problem we have. Single phase full bridge voltage source inverter shown in the figure has the output frequency of 50 Hertz. So output frequency of 50 Hertz. Unipolar pulse width modulation with switching frequency of 50 kilohertz. Switching frequency of this, I mean the device is in this voltage source inverter is 50 kilohertz. The modulation index is 0.7. V in is of 100 volt and L is given as 9.55 millihenry. C is 63.66 microfarad. R is 5 ohm. Okay. The amplitude of the fundamental component is the output voltage. In this output voltage, we need to find the fundamental component. Okay. Under steady state. What is the fundamental component available here? What is the fundamental component available here? For that, what you can do is you can apply, the peak value of the fundamental component available here will be modulation index MA into this VDC. Okay, so you can say that the output voltage, this voltage V out, okay, the output voltage has the fundamental component peak as 100 into MA, modulation index, and modulation index is 0.7. This is the peak value of the fundamental component available at this point. Okay, so it comes out to be 70 volt. 70 volt is the output voltage available here. Fundamental peak value. Okay, we have calculated this fundamental peak value. Now we need to calculate this voltage. So again, it's a circuit theory problem now. What is the fundamental frequency? Fundamental frequency is of 50 hertz. Okay, so this is the circuit we have, and this voltage has the peak value of 70 volts. So I can write it 70 angle 0, let's say. Okay, and the reactance of this inductor is J omega. Omega is 100 pi into L. L is 9.55 into 10 to the power minus 3. Okay, so this comes out to be, let's write it 100 pi into 9.55, okay, into 10 to the power minus 3. So it comes out to be 3 ohm, J 3 ohm. Okay, now let's find the capacitive reactance. So 1 by J omega is 100 pi into C, and C is 63.66 microfarad. Okay, so this comes out to be 10 raised to the power 12 divided by 100 pi into 63.66. Okay, so it comes out to be 5 into, obviously minus J, 5 into 1 2 3 4 5 6 7, 10 to the power 7 ohm. Okay, so this is the capacitive reactance of this capacitor. Oh, it's microfarad, excuse me. So 10 to the power minus 6 I have to write. Okay, so you can say that it will become 50 ohm, minus J 50 ohm. Okay, it will become minus J 50 ohm. Let me calculate this again. So yes, minus J 50 ohm. Okay, so now this reactance is minus J 50 ohm, this inductive reactance is J3, and this resistance is given as 5 ohm, and we need to calculate this voltage. We need to calculate the amplitude of the fundamental component under steady state. This voltage we need to find. So what you can do is you can apply network theory and you can calculate this voltage. How to do that? First, let's take the parallel of these two. So it will become 5 into minus J50 divided by 5 minus J50. Okay, this is the parallel combination of these two elements, and then J3 in series with that. So this is the equivalent impedance. Okay, 70 divided by Z equivalent will be the current I. Okay, 70 divided by Z equivalent. Let's find Z equivalent value. So it's 3 iota plus, in the numerator you have minus 250 iota divided by, in the denominator you have 5 minus 50 iota. Okay, and it comes out to be 5.58, 5.548. 5.548 at an angle of 26.84. Okay, this is the current, this is the Z equivalent. So the current will be 70 divided by this impedance value. Okay, so from here I can say that the net amount of current which will flow from here is 12.61 at an angle of minus 26.83, and whatever current will flow here, you can apply the current division rule to find this current. So let's apply the current division rule. So then the total current from the supply side is 12.61 at an angle of minus 26.83 into, we need to find this current, no? So this impedance has to be in the numerator, divided by the total impedance 5 minus j50. Okay, this is the current which will flow on this side. Whatever current is flowing on this side, multiply by 5 will be the output voltage. Okay, so let's calculate this output voltage. This current multiply by, okay, if you calculate all these values, then you will get the answer as, let me check the answer. So the voltage will become 25.10 volt. I don't know whether this is correct or not. 25.10. Okay, 108 volt. This is the peak value of the fundamental component available here. I have done everything correct in a correct manner. The only thing which I'm concerned is of calculation mistake. Okay, so please check my calculation mistake, whether I have done it, I mean whether there is some calculation mistake or not. So that is your part, you have to check that. Otherwise everything is perfectly fine. Okay, so I hope you understood this problem. Let's move to the next question, and the next question on your screen is this question number 22. Let me, yes, question number 22 you can see on your screen. So this question says the switches T1 and T2 in figure are switched in a complementary fashion. This is the switch T1 and this is switch T2. So they are switched in a complementary fashion with a sinusoidal pulse width modulation technique. The modulating voltage Vm is of 0.8 sine of 200 V. Okay, so this is the modulating voltage, and the triangular carrier voltage in figure B has the frequency 5 kilohertz. Okay, and the peak value of this triangular wave is 1. It is given as 1. Okay, the peak value of the 100 hertz component in the load current. Okay, we need to calculate the peak value of the 100 hertz component. 100 hertz is the fundamental component, remember, because you can see that the modulation voltage is this, and the omega is the omega naught. Whatever frequency this modulating voltage has, that frequency will be equal to fundamental frequency. Okay, so the fundamental frequency is 200 pi. It means the fundamental frequency in hertz will be 100. Okay, this is the fundamental frequency of the output voltage. Okay, so what I need to do is I need to find the peak value of 100 hertz component in the load current. This is the load current. So we need to calculate peak value of this fundamental component of this load current. How to do that? So again, I am giving you at least 2 to 3 minutes. 2 to 3 minutes I am providing you. It's 7 p.m. So I will discuss this problem at 7:03. Okay, do it fast, everyone. Solve this problem. It was asked in 2016. Solve it, everyone. Do it fast. Question number 22. I think time over. Okay, now it's my time. Okay guys, you can see that the modulation index is the peak value of this wave, okay, divide by the peak value of this triangular wave. So modulation index ME is 0.8, okay, and we know that the output voltage across this load will vary from, the output voltage you can see will vary from plus 250 to minus 250, okay. Output voltage will vary from plus 250 to minus 250, okay. What does it mean? It means the fundamental component of the output voltage, the peak value of the fundamental component of the output voltage is 0.8 into this 250, okay. So it will come out to be 200 volt. This is the peak value of the fundamental component, okay. We need to calculate the current, the peak value of the fundamental component of the current. So it's very easy peasy now. 200 divided by the impedance. So the impedance, the fundamental impedance is 12 plus J16. 12 plus J16. Okay, whatever this current is, this is the peak value of the fundamental current. Okay. It is asked the peak value of the 100 Hertz component. 100 Hertz means fundamental component. Okay. So this is the peak value of the fundamental current. It was easy peasy again. So you can calculate this value. Let me solve it for you. 200 divided by 12 plus 16 iota. Okay. So it comes out to be, we need only magnitude. So it will be 10 ampere. Okay. So the peak value of this current is 10 ampere. 10 ampere. So this was simple problem. Let's move to the next problem, guys. Next problem is question number 23. A single phase full bridge voltage source inverter is fed from 300 volt. Let me check whether the diagram is given or not. 23, question number 23. No, diagram is not mentioned. Only options are mentioned. So let's read the problem. And the problem is a single phase full bridge voltage source inverter. So when the diagram is not given, you have to draw the diagram. So let me draw the diagram for you. It's a single phase voltage source inverter. This is the single phase full bridge voltage source inverter fed from 300 volt. So let's say this is 300 volt battery. A pulse of 120-degree duration is used to trigger the appropriate devices in each half cycle. It means these devices are on and off for 120-degree only. Okay. It means the output voltage will be for 120-degree. The output voltage is plus 300 volt, and for next 120 it's minus 300 volt. Okay, this is pi. Okay, this is 120 and this is pi. So if you subtract 120 from 180, you will get 60. So out of 60, pi by 6 on this side and pi by 6 on this side. Okay, so you can see that pi minus pi by 6 is 5 pi by 6. Okay. So this is the output voltage which we will get, because it is mentioned a pulse of 120-degree duration. So this is the 120-degree duration. So we have to make it symmetric. That's why I have drawn like this. Okay. A pulse of 120-degree duration is used to trigger the appropriate devices in each half cycle. Now what we need to calculate is RMS value of the fundamental component. Okay. So we need to calculate the RMS value of the fundamental component. How to calculate? You can apply quarter wave symmetry. With the help of quarter wave symmetry, first calculate the peak value of the fundamental component and then divided by root 2 will be the RMS value of the fundamental component. So now let's apply quarter wave symmetry to calculate the peak value of this fundamental component. How to calculate that? So the peak value of the fundamental component will be 4 by pi integration from pi by 6 to pi by 2, 1 quarter. Okay. So from pi by 6 to pi by 2, this voltage is 300, and since this is an odd signal, sin omega naught t d omega naught t. Okay. This way you can calculate the peak value of the fundamental component. So it will come out to be 1200 by pi. Integration of sin omega naught t is minus cos, upper limit is 0, lower limit is cos pi by 6. So this is the peak value of the fundamental component. Divided by root 2 will be the RMS value of the fundamental component. Okay. Now you can calculate this value. It's easy peasy. Nothing to worry. So this was again a simple problem. Let's move to the next problem. Next problem on your screen is question number 24. Okay. And you can see this question number 24. We have a 3-phase voltage source inverter as shown in the figure is feeding a delta connected resistive load. So we have delta connected resistive load and 30 ohm per phase. Okay. It is fed from 600 volt battery. We have connected a 600 volt battery with 180-degree conduction mode of the solid state devices. The power consumed by the load we need to calculate. Again, it's a very simple problem. You have to spend like 2 to 3 minutes on this. Okay. And try to solve it. This was asked in 2016 and it is of 2 marks. Okay. So try to solve this question, guys. The time now is 7:08. I will disturb you at 7:11. Okay. Till then you have to solve this problem. At least spend some time, because when I'll solve all the problems. No worries in that. No problem in that. But it will give you nothing. Okay. Remember this. Whenever you pick the pen and you try to solve the problem, then only you will get some information. Okay. So my request is spend 2-3 minutes on this problem and then I will solve it. Okay. Do it, guys. So guys, it's my turn now. Okay, let's try to solve the problem. So the problem says we have a three-phase voltage source inverter. Okay, let me let's solve now. And the conduction mode is not provided to us, so by default we have to take 180-degree conduction mode. Okay, no, conduction mode is given, 180-degree conduction mode, it's given. Okay, conduction mode is 180-degree. Okay, so let's say there are two capacitors connected here. Let's assume that there are two capacitors and this point is grounded. Let's call it O. This point is at, with respect to O, this point is at 300 and this point will be at minus 300. Okay, now let's call this point as A because it is connected to leg A. This is B and this is C. So first we'll draw the voltage VAO. VAO means the voltage of this point with respect to this O point. Since the conduction mode is 180 degree, so for 180 degree this upper switch is connected to this upper point. It means the voltage has to be at 300 volt, and for next 180 degree the voltage has to be minus 300 volt. Okay, I hope it is clear. So it will be minus 300, wait, minus 300 volt. Okay, so this will be the voltage VAO, the point voltage, the voltage of this point with respect to this O point. Okay, with respect to this O point. Now what will the VBO? VBO will be shifted by 120 degree. If you can shift this voltage by 120 degree, then you will get VBO. Okay, let's shift the wave shape. So this is our VBO. Okay, and this is again minus 300 and this is plus 300. Okay, this is VBO. Now let's calculate VAB. VAB is VAO minus VBO. So VAB will be, VAB is equal to VAO minus VBO. So if I take the difference, you can see that for first 120 degree, this is 300 and this is minus 300. So if you subtract the voltage, this minus this, if you do that like this, it will become 600 volt. Okay, next 60 degree the voltage will become 0. Why? For next 60 degree, because it is 300, it is also 300. For next 60 degree it will become minus 600 volt. Next 60 degree it will become minus 600 volt. Okay, okay, and for next 60 degree it is again 0. So this will be the voltage wave shape. Okay, this will be the voltage wave shape. 600 minus 600, this is the line voltage. Now what I need to do is I need to calculate the RMS value of this line voltage, and with the help of that RMS value we can calculate the power loss in 30 ohm and then multiply with 3 ohm, multiply with 3. Okay, so that we can calculate the power consumed in 3-phase load. What is the RMS value of this? This is 0, this is pi by 3, this is 2 pi by 3 and this is pi. So if you rectify, the period will be pi. I mean, take the mode of this. If you take the mode of any wave, RMS value will not change. Okay, so take the mode of this wave, the period will become pi and the RMS value will be 1 by pi integration 0 to 2 pi by 3, take the square of that, 600 square d omega t. Okay, and take the root of this. So it will become 600 root 2 by 3. 600 root 2 by 3 is the RMS value of this line voltage. Now we need to find the power loss in this. To calculate the power loss, take the square of that, take the square of that, divide by 30. Okay, this is the power loss, multiply by 3. Okay, multiply by 3. So this is the power loss in this load. Now you can calculate this power loss in kilowatt as well. So what you need to do is just take this 10, and in the numerator you will have 3600, 4 zeros will be there, into 2 by 3 and divide by 10. Okay, this 10 factor will also be there. So this is cancelled, and if you, it will become 12,000 into 2, 24,000. So in kilowatt it will be 24 kilowatt. Okay, in kilowatt it will become 24 kilowatt. So this was again a very good problem. Question number 24, easy peasy. Okay, let's move to the next problem, guys. Next problem is question number 25, and you can see on your screen, a three-phase voltage source inverter is supplied from 600 volt DC as shown in the figure below for a star connected resistive load of 20 ohm per phase. Okay, so this is the load we have, 20 ohm per phase is the load. Okay, the load power for 120 degree device conduction. Now the conduction mode is 120 degree and the load is in star connection. Okay, we need to find the power loss in the load. So again I'm giving you 2 to 3 minutes to analyze this problem and then solve. Okay, so try to solve this problem, guys. You have 2 to 3 minutes. Right now the time is 7:18. I'll disturb you at 7:21. Okay, so from 7:18 to up to 7:20 at 21 p.m. you have to solve it. Okay, do it fast, everyone. Do it fast. Do it fast, everyone. Time over. Okay, now it's my turn. You must have solved this problem. Let's try now. Okay, so we have a star connected load. Wait. So this is the problem we have. Question number 25, you can see. So we have a star connected load, resistance is of 20 ohm, and we have a voltage source, 120 degree conduction mode. So let's say I connect two capacitors here with this point as grounded. Let's call it O point. So with respect to O, this voltage is of 300 volt and this voltage will be of minus 300 volt. Okay. Now let's call this point as A, this point as B, and this point as C. If this is A, this point will also be A, this point will be B, and this point will be C. Okay. Now let's first find A with respect to O. So if you write A with respect to O, VA with respect to O. Since the conduction mode is 120 degree, these are the 60 degree interval. For first 120 degree upper switch is closed. It means the output voltage will be 300 volt. I mean this voltage with respect to this O point will be at 300 volt. For next 60 degree, no switch is connected. Not this one, not this one. So this voltage will remain at 0 volt, let's say. And for next 120, it will be minus 300 volt. Okay. So this is the voltage of point A. This is the voltage of point A. Fine. VAO. This voltage is VAO. Now let's come to VBO. VBO. So we have to delay it by 120 degree. So if you delay it by 120 degree, the wave shape will look like this. I mean the 0 will come to 120 and the wave shape will look like this. So I have delayed it by 120 degree. Right? This is the voltage wave shape we'll see. This is minus 300 and this is 300. So this is VBO. Now what we can do is we can take the difference to calculate the line voltage. So let's calculate the line voltage. VAB. For every 60 degree we have to look. Okay, for first 60 degree this is 300 and this is minus 300, so it will become 600. Okay, for next 60 degree this is 300, this is 0, so the output voltage will be 300. Okay, 300 volt. Fine. For next 60 degree it is 0 and it is at plus 300, so the difference will be minus 300. Okay, minus 300. For the next 60 degree it is minus 300 and it is plus 300, so difference will be minus 600. Okay, for next 60 degree it is 0 and wait 60 60 180 and then 240, so 60 180 and then 240. Okay, from now onwards we have to see 0 60 this is 180 and this is 240. Okay, at this point we have 240. From 240 onward we have to see na 60. So this is 180 and after 180 you can see that this is minus 600. Okay, now from 180 to 240, 180 to 240 it is minus 300 and it is plus 300, so if you subtract you will get minus 600. Okay, now from 240 to 300, this is 240 to 300. From 240 to 300 it is minus 300 and it is 0, so if you take the difference you will get minus 300. Okay, so this is the line voltage we have. I hope you understood. I mean I have taken the difference of these two waves. This is the line voltage we have, right? And convert this star connected load into delta connected. So if I convert this star into delta, this will be the delta connected load and the value of this will be 60 and 60. You can see that. Okay, this point is at A, this point is B, this point is C, and we know this line voltage VAB. This is the voltage across the 60 ohm. Now what I can do is I can calculate the RMS value of VAB and take the square of that, divide by 60 will be the power loss in this 60 ohm, multiply by 3 will be the 3-phase power in this load, or you can say in this load. Okay, so this was again easy peasy. Only thing is we need to calculate the RMS value of this wave. How to calculate? You can take the mode of this. If you take the mode of this wave, RMS value will not change. Only thing is the period will become pi. Okay, so if you calculate the RMS value, it will become 1 upon pi integration from 0 to pi. Let's call this point as 0, and if this is 0, this will be the pi. Okay, so from 0 to pi by 3, take the square of 300 d omega t plus pi by 3 to 2 pi by 3, 600 square, plus 2 pi by 3 to pi, 300 square. Okay, and take the root of that. So what will be the RMS value? 300 square I have taken common. It will be pi by 3 plus 4 into pi by 3. So 4 pi by 3 plus pi by 3. Okay, and in the denominator we have pi, and take the root of that. This is the RMS value. Okay, so it will become 2 pi, and then so it will become 300 root 2. So the RMS voltage of the line voltage is 300 root 2. 300 root 2. Please check it. I think this is correct. Okay, 300 root 2. Now to calculate the power loss, what you need to do is take the square of that, divide by 60, and then multiply with 3. You will get the power loss. So again, this problem was very simple. Only thing is you need to apply the basic ideas. Okay, let's move to the next problem. Next problem on your screen is this, question number 26. Okay, question number 26 you can see on your screen. It says in the converter shown below, the switches are controlled such that the load voltage V0T is a 40 Hz square wave. Okay, the RMS value of the fundamental component of the V0T. I think it's very easy peasy. Okay, do it guys, do it everyone. I'm giving you 2 minutes for this. Okay, so wait. So I'm giving you 2 minutes for this. Solve it. Do it fast everyone. Okay, I think you must have done it. Now it's my turn. Tell me guys, have you done it? Okay, let's solve this problem. So RMS value of the fundamental component of V naught T. What is the wave shape of V naught T? So the wave shape of V naught T will be a square wave, and it will be 220 positive and then 220 negative. This will be 220 positive and then 220 negative, minus 220, right? Okay. RMS value of the fundamental component. So what is the fundamental component peak value here? If you calculate the fundamental peak value, then it will be 220 into 4 divided by pi. This is the peak value of the fundamental component of this voltage. Peak value of fundamental component of this voltage. Okay. Divided by root 2 will be the RMS value. So this was simple, very easy peasy. Okay. Let's move to the next. So next questions are on your screen. Question number 17 is I think 17 and 18 are the linked problem. Okay. Try to solve them. Try to solve these questions. Okay. Question number 17 and 18. Okay, do it fast everyone. And how much time I should give you is let's say 2 to 3 minutes for this problem and 1 minute for this problem. So in total you'll get 4 minutes. Okay, right now the time is 7:35 to, you can say, 7:40, let's say. Okay, I'm giving you 5 minutes. Solve it. This is a good question. Solve this problem, guys. Okay, I think you can check the answers as well. I mean, if you have the previous year problems, then you can check the answers as well. Okay, because I don't have the answers, because I have one book for the previous year questions, but the answers I don't believe on the answers provided by these books. Okay, so anyway, do it fast everyone. Do it fast, everyone. My turn. Time is over. So must have solved it. Let's see. Okay. So the voltage source inverter shown in the figure below is switched to provide 50 Hz square wave AC output voltage V0 across RL load. Okay. So this is the RL load and this is the output voltage V0. Okay. Wait. Now we can read. So the reference polarity of V0T and the reference direction of the output voltage I0 are indicated in the figure. R is given as 3 ohm and L is given as 9.55 millihenry. Okay. For the interval when V0 is negative and I0 is positive, the pair of devices which conduct the load is. Okay. So it says when V0 is negative, obviously the output voltage will be like this. And the current can take positive or negative value. Current in RL load will be like this. Okay. It says that when V0 is positive and I0 is negative. When V0 is negative, when V0 is negative and I0 is positive during this interval, okay, which the pair of devices which conduct for the load current, okay, we know that output voltage is negative when this Q3 and Q4 will conduct, okay, then the output voltage will be negative. But the problem is when these Q3 and Q4 are on, they will not be conducting. Why? Because the current cannot flow like this. I mean, the current cannot flow like this. This and then this. Why not? Because the current is positive. Current is not negative. This current is not negative. I mean, this current is in opposite direction. Na? If these Q3 and Q4 are conducting, they are on. That's for sure. They are on. That's for sure. But they are not conducting. So on condition and conduction condition are two different things. On condition and conduction condition. They are two different things. If the output voltage is negative, it means Q3, Q4 are on, that's for sure. Q3, Q4 are on, that's for sure. Then only the output voltage is negative, but they are not conducting. Since the current is positive, so in the load, the current has to be in the same direction. So diode D3 and D4 will conduct. Okay, you can see that when the current is flowing like this, Oh, you can see that since the current has to be in this direction, na? Current has to be in this direction, so current is flowing like this. Now what are the possibilities that current can, how the current can flow in this direction? Okay, Q1 and Q2 are off, they are off for sure. This current cannot come from this diode. Obviously this current will flow through this diode D4. They are on, but diode D4 is conducting, then only the current will be in positive direction. Similarly, in Q3 diode D3 will conduct. Okay, these are on devices. Q3 and Q4 are on, that's for sure, but diode D3 and D4 are conducting. Okay, so D3 D4 are conducting. Answer is D. Okay, I hope you understood it. So which pair of devices will conduct the load? D3 D4. Okay, conduct, he's asking conduct about conduction. So conduction is diode D3 and D4 are under conduction mode. Okay, okay, let's move to the next question. The next question says, question number 18. Okay, question 18, let's read the statement. For appropriate transition, it means zero voltage switching and zero current switching of the IGBT during turn on turn off phase. Okay, so if you want to turn off or turn on, for appropriate transition, it is written appropriate transition. It means zero voltage switching or zero current switching of the IGBT during turn on or turn off phase. While turning on or turning off the device, which switching is required? Okay, options are zero voltage during turn off and then zero voltage switching during turn on. Next is zero current switching during turn off and zero current switching during turn on. So I think zero current switching during turn off is correct answer. Why it is correct? Actually it's a memory based question. Okay, so you have to remember it. The only thing is we need to minimize the switching losses. Okay, so to minimize the switching losses, we need to apply this zero current switching during the turn off. Okay, so that you should remember. Okay, it's a memory based question. You can leave this question for the time being. So let's come to the next question, guys. So the next question on your screen is question number 19. Okay, question number 19. Try to solve this problem. It's again a very good problem. Okay, question number 19. The figure shows one period of a output voltage of an inverter alpha to be chosen such that alpha is between 60 and 90. If the RMS value of the fundamental voltage is 50 volt, then the value of alpha in degrees. So we need to calculate the value of alpha in degrees. RMS value of the fundamental component is 50 volt. Okay, and one period is shown in the figure. This is 0, this is 180, and this is 360. Okay, so we need to calculate the RMS value of the fundamental component. RMS value of fundamental component is given as 50 volt. We need to calculate alpha. Okay, so do it, guys. Take 2 to 3 minutes. Take 2 to 3 minutes for this problem. Solve it. Do it fast. It's a simple problem. Okay, you can apply symmetry conditions to calculate that. Okay, in the previous question, the answer is given as D. Okay, the answer is given as D. You have to be careful. You have to remember that. Zero current switching during turn on to minimize the switching losses. Okay, this has to be the correct answer. Okay, so please correct it. Nothing to understand. The only thing is during switching we need to minimize the losses. To minimize the loss, when you turn on the device, then the current through the device has to be 0. Okay, otherwise there will be some switching losses. So this is the basic idea that you need to remember. So answer is D, and just remember this. Okay, nothing conceptual in this problem. Okay, let's come to the next problem, 19. Do it fast, everyone. Okay, let's try to solve this problem. Question number 19. Now I think we can solve it. Okay, see, this is the origin, okay, and this is 180 degree, okay. Now you can see that if I repeat the wave in negative direction, then this wave will repeat, okay, and accordingly I can say that this wave contain odd half wave symmetry. This is odd and contain odd half wave symmetry, okay. Now this has to be the pi by 2. So the signal is odd and contain odd half wave symmetry. So you can say that this contain quarter wave symmetry. Okay. If you apply the concept of quarter wave symmetry, you can calculate the RMS value of the fundamental component. How? Peak value of the fundamental component is 4 by pi from 0 to pi by 2. This voltage V0 t into sine of omega naught t d omega naught t. This is the peak value of the fundamental component. So what you can do is you can break this 4 by pi from 0 to alpha. Output voltage is 100. So 100 sine omega naught t d omega naught t. Okay. From alpha to pi by 2. From alpha to pi by 2, output voltage is minus 100 sine of omega naught t d omega naught t. Okay. So if you try to solve it, it will become 400 by pi. 400 by pi. Integration of sine omega naught t is minus cos, upper limit minus lower limit is 1 plus cos alpha. Similarly, integration of sine omega naught t is minus cos omega naught t, upper limit minus lower limit, so it will become double. Okay, so this is the peak value of the fundamental component. You can divide it with root 2 to get the RMS value. Okay, and the RMS value has to be equal to 50 volt. Okay, so you can put it equal to 50 volt. Now you can calculate the value of alpha. Okay, So 1 plus 2 cos alpha will be equal to 50 root 2 into pi divided by 400. Okay, 50 root 2 pi divided by 400 is 1 plus 2 cos alpha. From here you can calculate the value of alpha. Easy peasy. Okay, let's move to the next problem. Let's move to the next problem, and the next problem is on your screen. Question number 20. Wait, let me minimize this. Yes, question number 20 you can see on your screen. Okay, a single phase voltage source inverter shown is feeding the power to a load. Okay, so this is the voltage source inverter. The triggering pulses of the devices are shown in the figure. Okay, so these are the two capacitors, this is VDC, these are the switches. Current is sinusoidal. Okay, he is saying that this load current is sinusoidal and is 0 at 0 pi 2 pi. The node voltage VAO is the voltage at this point with respect to this O point, has the wave shape. I mean, we need to calculate the wave shape of this load voltage. Okay, so wave shape of VAO, this is A, this is O. Let's ground it, no problem. Okay, because one point I have taken, I can take as reference, so let's call it at 0 volt. So we need to draw the voltage of this point A with respect to O. It is given that the load current is sinusoidal and 0 at 0 pi 2 pi 3 pi 4 pi. Okay, at these instant the load current has to be 0. Now we need to solve this problem. So it's a 2-mark problem and not very difficult, so it's easy problem. At least spend 3 to 4 minutes on this. Okay, now the time is 7:56. I will disturb you at 8 p.m. Okay, so try to solve it. Do it guys, do it fast, everyone. Do it fast, at least have some conceptual understanding of this problem, then I will solve it. Okay, I will try to read the problem, think about it. Even if you are not able to solve it, just first read it and try to understand it. Okay, try to spend some 2-3 minutes on this problem, and after that I will solve it. Okay, do it fast, everyone. Okay, let me solve it for you. So when you switch on S1 S2 like this, from theta to pi minus theta, S1 S2 S1 S4 are on. So output voltage is VDC by 2, VAO will be VDC by 2, okay, because we need to find the VAO na. VAO will be VDC by 2 because this switch is closed na, from theta to pi minus theta. So this point has the upper level voltage, and the upper level voltage is with respect to this O point, it is VDC by 2. So VDC by 2 from theta to pi minus theta, and then this will be the pi value, and then from pi plus theta to 2 pi minus theta. Okay, S3 is closed. It means this point voltage has to be minus VDC by 2. Okay, minus VDC by 2. This will be the output voltage. The load current is sinusoidal and is 0 at 0, pi. At this point, at this point, at this point, load current is 0. Okay, load current is 0. Now you can see that the load current is sinusoidal. It means, let's say it's a fundamental component. Load current is like this. So if I draw the wave shape like this, if I take the voltage wave shape like this, then the output voltage cannot be like this. VAO cannot be like this. Why? Wait a minute, my system is down, so let me restart it. I mean, this screen is down. There is some point. Okay, yeah, come light. Okay, so now if this is the current wave shape, this cannot be the output voltage. Why? This cannot be VAO. Why? Because if you see, during this interval, current is positive and voltage is positive, because this is closed. Okay, this switch is closed and current is positive, moving in this direction. So probably the current will flow from S1 to S4. Okay, because S1 S4 are on na, from theta to pi minus theta. So this output, this voltage will be plus VDC by 2 and current is flowing in positive direction, right? But what about this? During this interval, current is positive, but S1 is not on. Current positive means current has to flow. It can only flow via these two diodes. The positive direction current can flow only because this switch is off. From 0 to theta, this switch is off. Obviously, these two switches are also off, but still the current is positive in this direction. So obviously, diode D1 and the diode D3 and D2 will be conducting. If diode D3 D2 will be conducting, it means this point voltage has to be minus VDC by 2. Why minus VDC by 2? Because it is connected to a lower level. With respect to O, this has to be minus VDC by 2. Okay, so during this interval, it has to be minus VDC by 2. Similarly, from pi minus theta to pi, again minus VDC by 2, because current is positive. Okay, so only way is D3 D4 are conducting. Okay, so minus VDC by 2. Now there is only one option which has this negative part. Okay, so answer is D. Delhi is the correct answer. Okay, I hope you understood it. So this was again a very good problem. Let's move to the next problem. You can see on your screen, and let me, okay, wait. So we have question number 12 and 13 you can skip, because this 13, I mean, you can skip this problem. Why? Because this is based on, I mean, these are the old problem. Syllabus has changed. I mean, nowadays nobody asks about these type of inverters. Okay, so You can skip this. Rather, you can solve the problem. Let me tell you which problem you need to solve. You need to solve problem number this. Okay, this problem you need to solve. Wait, let me. Okay, so you should solve problem number 15 and 16. Okay, 15 and 16 you should solve. It's a common data problem. You can see that in a three-phase inverter, the load is balanced and it is connected in star mode, and 180-degree conduction mode is there. All the devices are ideal. The RMS value of the load phase voltage is, okay, phase voltage RMS value we need to calculate, and then power consumed by the three-phase load, that we should also calculate. VD is 300 volt. It is 300 volt. Okay, we have to take this as 300 volt. Now try to solve this problem, and I mean, it will take some time, so I'm giving you some break, and during the break you have to solve these two problems. Okay, problem number 15 and 16, these are the relevant problem for your GATE exam. Okay, these two problems you have to solve, and right now the time is 8:05. I'm giving you a break of 10 minutes. 8 to 10 p.m. there is a break. Okay, so no, 8 to 10:15. I'm giving you 10 minutes break. 8 to 8:15. Okay, so this is the break. After 8:15 I'll discuss these two problems. Okay, and then we'll come to DC-DC converter. We'll discuss the problem related to DC-DC converter. Okay, so guys, try to solve these problems in this break, and see you after the break. Okay, so now we can solve the problem. I hope you must have done these problems. Let's solve this problem first. So let me move to this side. Okay. So the load is star connected and the conduction mode is 180 degree. Okay, we need to calculate the RMS value of the load phase voltage. Okay, so what I can do is I can say that this is A point, and let's connect capacitors as well. Okay, and put this middle point as ground. So this will be 150 with respect to ground, and this point will be minus 150 volt. Okay, so this is A, this is B, and this is C. Okay, if we write VA with respect to O, this is the A point voltage, this is A point, so this point will also be A, this will also be B, and this point will be C. So if you write the voltage of this point with respect to this O point, VAO, then that will be plus 150 and minus 150. Okay, for 180 degree it's plus 150, and then next 180 degree will be minus 150 degree. Okay, this will be the voltage of point A with respect to O. Okay, similarly we can calculate VBO. For VBO we have to delay it by 120 degree. Okay, we have to delay it by 120 degree. It means each interval is of 60 degree. Okay, these are the interval, each interval is of 60 degree. So if I delay the wave by 120 degree, then this will be the wave, this will be the wave. Okay, this is VB with respect to O. Okay, and what will be the VCO? VCO will be, you can just advance this voltage by 120 degree. So each interval is of 60 degree. If I advance this wave by 120 degree, then this point will be at 0. Okay, so the wave will look like this. Okay, VAO, VBO, and VCO. Okay, perfect. Now what I can do is I can calculate the phase voltage, but first to calculate the phase voltage, what we need to do is we need to calculate this point voltage. Okay, if we can calculate this point voltage, then this phase voltage will be known to us. How to calculate this neutral voltage, this point neutral voltage, Vn? So let's draw the voltage Vn. For every 60 degree we have to find Vn. Now how to do that? We can apply nodal. Okay, for first 60 degree interval, if you see, this is the resistive load, this is the resistive load, this point is at N, so this is Vn voltage. Okay, what about this? This is VAO. For first 60 degree it is 150. For next this point is VBO, this is minus 150, and this is VCO, it is 150. For first 60 degree interval, you can see that this is 150, this is minus 150, and this is plus 150. Okay, we can calculate Vn with the help of nodal. So coefficient of Vn is 3 by R, and that will be entering current 150 by R, minus 150 by R, and 150 by R. So simply it will become 150 by R, because these two will cancel. Okay, R will be cancelled, and then Vn will be 150 by 3. So it comes out to be 50 volt. Okay, 50 volt during first 60 degree interval. For the next 60 degree interval, you can see that this is 150, this is minus 150, and this is minus 1. Two are minus 150 and one is plus 150. So overall, again you can apply the nodal, and then it will be minus 150, and then it will become minus 50. Again next 60 degree it will be 50, and so this will be the voltage level at Vn. You just apply nodal. With the help of nodal you can see that the voltage at this point will be this way. Now let's calculate this phase voltage, Va minus Vn, and this is the N voltage with respect to O. So let's find VAN phase voltage. For every 60 degree, let's calculate the phase voltage. For first 60 degree, VAO is 150, okay, and this is 50. So if I take the difference, it will become 100 volt, okay. For first 60, 100 volt. Next 60, this is 150 and this is minus 50. So if I take the difference, it will become 200 volt. 200 volt. For next 60, it is 150 and it is 50. Again difference 100 volt, okay. For next 60, it is minus 150 and it is also minus 150. So it will become minus 60 60 60 60 60 60. Okay, for next 60 degree interval, it is minus 150 and it is also minus 150. So if I take the difference, you'll get minus 100. You'll get minus 100 and then minus 200. I think this is the wave shape you will get. Okay, this is the wave shape of VAN. Okay, so it was simple. We have calculated VAN. Now we need to calculate the RMS value of this. How to calculate the RMS value of this? RMS value cannot be 280, cannot be 212, because it cannot be more than 200, na? Okay, either it is 106 or 141.4. okay, these two options, out of these two options you have to, I mean B will be correct, because I mean you can see that this is the pi period, because if you take the mode of this wave, the period will become pi. So the RMS value will be 1 by pi from 0 to pi by 6, 0 to pi by 3, 0 to pi by 3, 100 square d omega t, plus pi by 3 to 2 pi by 3, 200 square d omega t, plus 2 pi by 3 to pi, it is again 100 square d omega t. Okay, and then take the root of that, root of this entire quantity. This will be the RMS value. So if you take 100 square com out of this, then you will get 100 out of this, and inside the root you will have 1 upon pi into, this will be pi by 3 plus this will be 4 into pi by 3, 4 pi by 3, plus this will be again pi by 3. Okay, you will get this. Now this is 6 pi by 3, so 100 root 2. 100 root 2 is the correct answer. Root 2 is 1.414, so the answer is Bombay. So again, this was an easy problem. What you need to calculate? You need to calculate this phase voltage. And to calculate the phase voltage, you must know this point voltage with respect to O and this point voltage with respect to O. First you calculate VAO, VBO and VCO. Once you get these three voltages, then with the help of nodal you can apply nodal and calculate this point voltage VNO, neutral point voltage with respect to O. Okay, and then take the difference, VAO minus VNO, that will be the phase voltage. Okay, so the phase voltage wave shape will be like this. If you take the mode, RMS value will not change, only the period will become pi. Okay, and then calculate the RMS value. So answer is Bombay. The next question is, if the DC voltage of 300 volt, the power consumed by three-phase load is, we know the RMS phase voltage. We know the RMS phase voltage, which is 100 root 2. So what is the power loss in this load? So 100 root 2, it is the RMS voltage across this load. Take the square of that, divide by the resistance value, and the resistance is 20 ohm. Divide by 20 and multiply with 3. This is the power loss that will occur across this entire load. Okay, 3 into Vrms square upon R. Okay, so you can easily calculate how much kilowatt is this. So it's up to you now. Okay, I hope you understood these problems. Now let's move to the next problem. So next chapter I'm starting is DC-DC converter. Okay, because I have almost 1.5 hour, so for the next 1.5 hour I want to discuss DC-DC converter. So the problem on your screen are question number this 28 and 27. It was asked in 2021 2 marks problem, and it was asked in 2021 2 marks problem. Again, it means in 2021 4 marks problems were there from this DC-DC converter. Imagine. So let's try to solve these problems. Spend some time, I mean 2 to 3 minutes for this question and 2 to 3 minutes for this question. Okay, I'm giving you almost 5 to 6 minutes. Think about these problems and try to solve them. Okay, everyone, please spend some time. Do it fast. It's 8:26 now. I will discuss these problems at 8:31. Okay, 8:31 p.m. I will discuss these problems. Till then you can solve these problems. Do it fast, everyone. Do it fast, everyone. Try to solve these problems. One more minute. Actually, 2 more minutes. Okay, I think it's my turn now. You must have solved these questions. Okay, let's see first this 2021 question. So the question says, consider a buck boost converter shown in the figure. So this is the figure of buck boost converter. Okay, right. The switch Q is operating at 25 kilohertz and 0.75 duty cycle. Assume the diode and switch to be ideal. Under steady state condition, the average current flowing through the inductor. So we need to find this ILT average. Okay, this we need to find. Okay, duty cycle is 0.75. Okay, so how to calculate this? First of all, we need to check whether the conduction is continuous or not, because if the conduction is continuous, then only we can calculate this average current. Okay, so how to check conduction is continuous or not? Assume that the conduction is continuous. If the conduction is continuous, then the output voltage will be, output voltage is this. When since it is a buck boost converter, so you can say that the output voltage will be D divided by 1 minus D. Okay, if the conduction is continuous, so it will come out to be 3 by 4 divided by 1 minus 3 by 4 is 1 by 4, so it come out to be 3. It means the V0 will be equal to 3 times of, this is V0 T upon VST. Okay, this is the ratio, D upon 1 minus D. So VST is 20, so 20 into 3 is 60 volt. Okay, you can check this. So this has to be 60 volt if the conduction is continuous. I am assuming that the conduction is continuous. If the conduction is continuous, then this output voltage divided by this input voltage has to be D upon 1 minus D. Since D is given as 0.75, so you can put the value 75 as 3 by 4. 3 by 4 divided by 1 minus 3 by 4. 1 minus 3 by 4 is 1 by 4. So it will come out to be 3. From here we can calculate V0 as 3 into Vs, 3 into 20. So it's 60 volt. If it is 60 volt, then I0 has to be 6 ampere. This current has to be 6 ampere. Okay, and we know that if the conduction is continuous, then the same ratio will be Is upon I0. If you know I0, then you can calculate the average value of this current, source current. And the average value of the source current will be whatever the average current we have at the output multiplied by 3. So the average value of this current has to be 18 ampere. 6 into 3, 18 ampere. Okay. So the average value of this inductor current will be this average plus this average, because from the diode this average current cannot go through the capacitor, because average current of the capacitor will always be 0. This current can only flow through this diode. It means the average current through this diode has to be 6 ampere, and from this side the average current is 18 ampere. So this current average value has to be 18 plus 6. It means it is 24 ampere. But this answer is true only if the conduction is continuous, and we don't know whether the conduction is continuous or not. So what we need to do? We need to find this IL min. Okay. If IL min comes out to be negative, then we can say that the conduction is discontinuous. So first let's assume that the conduction is continuous and draw the inductor voltage. What will the inductor voltage? This is the polarity of the inductor voltage. When the switch is on, the inductor voltage is 20. Okay. And when the switch is off, the inductor voltage will be minus 60. It will be minus 60. Okay. This will be the inductor voltage, right? Because when the switch is on, this is in parallel with the inductor. When switch is off, this voltage will be in parallel with the inductor with the help of, the diode will be sorted, and you can say that the output voltage will be in parallel with the inductor. But since the output has opposite polarity with compared with the inductor voltage, then the inductor voltage has to be minus 60 volt. Okay. Now if I draw the wave shape of current, then this has to be the current wave shape. I say that this is 𝐿min, this is 𝐿max, and the change in IL will be, you can integrate it, okay, and inductor voltage is 20 dt from 0 to dt, from 0 to t on time. This is 0, this is dt time, okay. So from 0 to dt you can calculate, so it will become 20 into 0.75 into t, okay. This is the delta IL, change in inductor current, okay. So what will be this value? It will be 15t. I think this is correct. 15t. 15t is the delta IL value. Now what is 𝐿min? What is this 𝐿min? How to calculate this 𝐿min? Minimum inductor current, 𝐿min. How to calculate that? 𝐿min is average inductor current minus delta IL by 2, okay. And what is average inductor current? Average inductor current, if the conduction is continuous, then we have calculated, and that current is, average inductor current is, tell me, 18 from this side and 6 from this side, 24. 24 is the average inductor current minus delta IL by 2, 15t by 2. 1 by L should also be there. 1 by L should also be there, okay. So this is the delta IL by 2, 24 minus delta IL by 2. Now check this, whether this is positive or negative. If it is negative, then this answer, average inductor current, which is 24, it will be wrong, because we have calculated this as average current only if the conduction is continuous, okay. So we have calculated the 𝐿min current, okay. The 𝐿min is 24 minus 15t by 2L. So what you can do is, you can calculate this 15 upon 2 into LF. L is 1 millihenry and F is 25 kilohertz. So milli and kilo will cancel, it will become 25, okay. It will become 25. You can see that 1 by F into L. L is millihenry, this is kilo, so kilo and milli will cancel. So you can see that this is positive, 𝐿min is positive. If 𝐿min is positive, then you can say that the conduction is continuous. It means the average inductor current is 24. It is the correct answer, okay. So first you have to assume that the conduction is continuous. With the help of that, calculate this average current, but then you should calculate the 𝐿min also. And 𝐿min is IL average minus delta IL by 2. Delta IL is IL peak, IL max minus 𝐿min. That is the delta IL value, okay. So you have to take delta IL by 2, okay. Let me check whether everything is fine or not. 15t by L. I think everything is correct, okay. So this is positive, it means conduction is continuous, and the average current has to be 24 ampere. I hope you understood it. This was again a very good question, okay. Let me check the answer as well, because I have the answers also for buck boost converter. Actually I have the options, which option is correct, so maybe the numerical answers will also be provided. Yes, 24 is the correct answer, okay. Yes, on communication, PYQ session will also be there, don't worry. At right time you will get that, okay. Let's move to the next question, guys. Let's move to the next question. And the next question on your screen is this. Question says, consider a boost converter. So we have the boost converter, and switch Q is operating at 25 kilohertz. Switch Q is operating at 25 kilohertz and duty cycle is 0.6. Assume the diode and switch to be ideal. Under steady state condition, average resistance are in as seen by the source. It is the average resistance seen by the source. Source is on this side, na? So how to calculate average resistance seen by the source? It's very simple. If you can calculate the average source current, then the average resistance seen by the source will be 15 upon IS, okay. That will be the average resistance seen by the source. Easy peasy, okay. 27 1 point, okay, 27 1.6 ohm, okay. I'll check it, Karthik. Let's see whether this is correct or not. So we have to calculate this IS value. Now how to calculate IS? Duty cycle is 0.6. So what we can do is, first we will apply, we will assume that the conduction is continuous. Nothing is mentioned in this problem whether the conduction is continuous or not. So let's assume that the conduction is continuous. Continuous conduction. Okay, let's assume that. If I assume that the conduction is continuous, then the output voltage will be, output upon input voltage will be equal to 1 over 1 minus D, because it's a boost converter. Okay, and D is given as 0.6, so you can put it as 0.6. It will be 1 over 0.4, so it will become 2.5. okay, it will become 2.5. V0 will be equal to Vs into 2.5. Vs is 15 into 2.5. okay, so it will become 37.5, right? V0 is 37.5 if the conduction is continuous, remember that. Okay, now if V0 is 37.5, divide by 10, so this current will be 3.75 ampere. Output current, output average current. So we know that this ratio is IS upon I0 also. We know I0, we can calculate IS. Okay, average source current will be 2.5 into this I0. I0 is 3.75. okay, and this value comes out to be 2.5 into 3.75. so it comes out to be 9.375 ampere. okay, this current comes out to be 9.375 only if the conduction is continuous, and the resistance seen will be 15 upon 9.375. so 15 upon 9.375 is equal to 1.6 ohm. But we don't know whether this option is correct or not. We don't know whether this answer is correct or not. Why? Because we don't know whether the conduction is continuous or discontinuous. We have to check. If the conduction is continuous, then this answer is correct. But if the conduction is discontinuous, this answer is wrong. How to check whether the conduction is continuous or discontinuous? Calculate the inductor current, IL_min, minimum inductor current, and check whether it is positive, negative, or zero. If it is positive, then the conduction is continuous. If it is negative, conduction is discontinuous, and if it is zero, conduction is just continuous. So let's calculate IL_min. How to calculate IL_min? First, let's see the inductor voltage, VLT, this polarity voltage. When the switch is on, this voltage comes across inductor, so the voltage will be 15. okay, during this on period, during this DT period, inductor voltage is 15. When the switch is off, this side is 15 and this side is 37.5. okay, because when this is off, and let's say this is grounded, okay, so you can see that when this is off, this side will be at 15 volt, and since diode is conducting, when this device is off, diode will be conducting, so this point voltage will be available here. It means this is 15, this is 37.5. so if you take the difference, you will get 22.5 minus 22.5. okay, minus 22.5. this is T. okay, so this will be the wave shape of inductor voltage. I hope you understood it. okay, so this is the voltage across inductor. Fine. Now if you look at the current wave shape, this will be the inductor current wave shape. Let's first calculate delta IL. So delta IL will be equal to 1 by L integration 0 to dt, and the voltage across inductor is 15. So it will become 15 into 15 by 10 to the power minus 3 into dt, and d is 0.6. okay, so if you multiply d into 15, so you'll get 9. okay, 9t, and t you can write as f. F is 25 kilohertz. Kilo and milli will cancel, so you'll get 9 upon 25. okay, 9 upon 25. This is delta IL. Now what is IL_min? IL_min is average inductor current minus IL by 2. IL mean is average inductor current minus delta IL by 2. Now what is average inductor current? What is average inductor current? Average inductor current is IS itself, because source current and inductor current will be same. So the average inductor current is IS. Since we are assuming continuous conduction and the average IS is 9.73, so you can say that it is 9.375 minus delta IL by 2. Delta IL is of this value. You can clearly see that if you take this value, I mean if you calculate this value, it will become positive. It will come out to be positive. It means IL mean is positive. And we know that if IL mean is positive, conduction will remain continuous. So our assumption was correct, and the calculation was also correct. Okay, so we have checked whether the conduction is continuous or not. Since the conduction is continuous, so you can say that the calculated value is correct. Okay, so let's move to the next problem. Next problem on your screen is this question number 22, 23. Okay, try to solve this problem, guys. Let me magnify this so that you can clearly see that. Okay, so question number 22. Let's first solve question number 22. Okay, and I'm giving you some time for this problem. Okay, take 3 to 4 minutes. Take 3 to 4 minutes for this problem. It's 8:47 and I will disturb you at 8:51. Okay, 8:47 to 8:51 you have to solve this problem. Okay, you have 3-4 minutes for solving this problem. Do it, guys, do it fast. Do it fast, everyone. So now it's my turn. Have you done it? Everyone tell me. Have you solved the problem? Question number 22. It's an easy problem. Do it fast. Do it fast. Okay, let's solve the problem. So in this problem, we have two buck converters connected in parallel. Okay, this is one buck converter. Okay, wait. The letters are. Okay, let's see the problem. So there are two buck converters connected in parallel. Okay, this is one buck converter and this is the other buck converter. Okay. The common input DC voltage of the converter has this is 100 volt. It is the common input. Load is 1 ohm and capacitor voltage has negligible ripple. Both converter operate in continuous conduction mode. The switching frequency is 1 kHz and the switch control signals are shown. Okay, these are the control signals. I mean 0.5 millisecond S1 is on, and then again next 0.5 millisecond S2 is on. Okay. The circuit operates in steady state assuming the converters share the load equally. Okay. The average value of this source current IS1, or you can say switch current IS1. Okay. So this average current we need to find. How to do that? Given that the conduction is continuous and input voltage is of 100 volt, okay, and duty ratio is half. If you can see, for S1 duty ratio is half. For S2 also duty ratio is half. So if you look at this converter, you can say that the output voltage has to be 50 volt. Okay, because the conduction is continuous. So this voltage has to be 50 volt, right? Okay. Now what we can do is, we know that the average current is 50 ampere. Average current is 50 ampere. And the power loss in this resistor is 2500 watt I square R. Okay. Since the load is shared equally, so you can say that out of this 2500 watt, 1250 watt is shared by this upper DC-DC converter and 1250 watt is shared by this lower DC-DC converter, because they are connected in parallel. It means this upper DC-DC converter will deliver the power 1250 watt and the input voltage is of 100 volt. So how much average current it will supply via this buck converter? 1250 watt divided by 100. It means 12.5 ampere. 12.5 ampere will supply. 12.5 ampere will be supplied by this upper buck converter, and 12.5 will be supplied by the lower buck converter. And this is the average current. Remember. So average value of this IS1 is 12.5 ampere. Okay. I hope you understood it. Tell me, guys. So this was again an easy peasy problem. So you can easily solve this. Let's move to the next question, number 23. Okay, let's move to question number 23. Question number 23 you can see on your screen. Okay, so the question is, a DC-DC buck converter operates in continuous conduction. Okay, it is given that the conduction is continuous. DC-DC buck converter is there. Okay, it has 48 input voltage and feeds a resistive load of 24 ohm. Okay, perfect. Switching frequency is 250 Hz. The switch on duration is 1 millisecond. The load power is asked. So try to solve this problem, everyone. It's a simple problem and I am giving you 2 to 3 minutes for this. 2 to 3 minutes for this problem. Try to solve it. Do it fast. Do it fast. Do it fast, everyone. I think it's time to solve. Okay. A DC-DC buck converter operates in, wait, now it is visible. Okay. A DC-DC buck converter operates in continuous conduction mode, has 48 volt input. Okay, so input voltage is 48 volt. Load RL is of 24 ohm. Switching frequency is 250 hertz. Switch on duration is 1 millisecond. Switch on duration is D into T. You can say that D by F, 10 to the power minus 3. So you can say that D is equal to 0.25 because F is 250. Na? So if you multiply F with 10 to the power minus 3, you'll get 0.25 D. So duty ratio is 0.25. Input voltage is 48. Since it is a buck converter, so the output voltage will be 0.25, which is 1 by 4 into 48. So it comes out to be 12 volt. So the output voltage is 12 volt. Across this RL, we have 12 volt. Now, what is the load power? Load power is 12 square divided by 24. Okay. So it will be 6 watt. Answer is 6 watt. Answer is Calcutta. Easy peasy. Let's move to the next question. Next question on your screen is a DC-DC boost converter is there. Okay. Duty ratio is controlled to regulate the output voltage at 48 volt. It means the output voltage is kept constant at 48 volt. We have to change the duty ratio. Okay. The input DC voltage. The input DC voltage is 24 volt. Okay. So let me write everything on this side. It is given that we have a DC-DC boost converter. So DC-DC boost converter. So we have boost converter. Okay, we have DC-DC boost converter. Output voltage is maintained at 48 volt. Okay, and input DC voltage. What is the input DC voltage? Input DC voltage is 24 volt. V in is 24 volt. Okay, the output power is 120 watt. P out is 120 watt. Output power is 120 watt. Okay, wait, output is 120 watt. The switching frequency is 50 kilohertz. Okay, switching frequency is 50 kilohertz. Assume ideal components and very large output filter capacitor. Okay, capacitor is very large. The converter operates at the boundary between continuous and discontinuous conduction mode. It means the conduction is just continuous. We need to find the value of the boost inductor. We need to find the value of the inductance. L, inductor we need to find. Okay. Now how to calculate this? How to solve this problem? L we need to find. Find L. To calculate this, first let's draw the boost converter. I think this is the boost converter. Tell me guys. This is the diagram of the boost converter. Input voltage is 24 volt. Okay, and output voltage is 48 volt. Conduction is just continuous. Just continuous means continuous itself. Okay, so you can say that 48 upon 24, output upon input, is equal to 1 over 1 minus D. This is cancelled with 2, so 1 minus D is half. D will become half. Okay, duty ratio is half. D is half. Okay, perfect. Now the P out is 120 watt. P out means this I0 into 48. I0 into 48 is 120 watt. So I0 comes out to be 120 divided by 48. Let's cancel this. It comes out to be 2.5 ampere. Okay, I0 comes out to be 2.5 ampere, right? Okay, V0 is 48, I0 is 2.5. We need to calculate the value of L. Now how to calculate the value of L? Because the conduction is just continuous, IL min is 0. Okay, so how to calculate IL min? We know that this current is 2.5. What about this current? This ratio is equal to IS upon I0. Okay, so if I multiply I0 by this factor, you'll get IS. So this current, average current is 5 ampere. This average current is 5 ampere. Okay, what about the inductor average current? 5 ampere average current is flowing like this. Out of that, 2.5 average current is going like this. So average inductor current has to be 2.5 ampere. This is the average inductor current. Okay, average inductor current is 2.5. Now what is IL min? IL min is average inductor current minus delta IL by 2, and this IL min has to be 0. Why this IL min has to be 0? Because conduction is just continuous. Okay, it means IL min has to be 0. So you can say that delta IL is 2 times of IL. It comes out to be 5. Okay, 2 times of IL. IL is 2.5. So it means delta IL has to be 5 ampere. Okay, and how to calculate delta IL? During this on condition, if you see, inductor voltage is 24 volt during this on condition. So current will change like this. Inductor current will change linearly from 0 to this value, and this change in current, we know that it's 5 ampere. So what I can do is, I can write the change delta IL as 1 by L integration 24 dt from 0 to dt. Okay, so it will be 24 dt by L. This is delta IL, and it comes out to be 5. So from there you can calculate the value of L. It comes out to be 24 d. D is half. okay, upon LF upon 5 into F. F is frequency, and frequency is given as 50 kilohertz. So kilo is converted to milli. Okay, so this will be the value of L. Now let's calculate this. So it is cancelled 0.1, okay, and 2.4 upon 50 millihenry. So the answer is 2.4 upon 50 millihenry. You can write it like this: 0.24 divided by 5 millihenry. Okay, so you can easily calculate this value. So it will be 0.048 millihenry. This should be the value of inductance. The only requirement was the calculation. Okay, otherwise the problem was simple. So let's see. In microhenry the problem is asked. So microhenry is 48 microhenry. Okay, in microhenry it will become 48. Let me check the answer. The answer is given as which question is this? 24. 48 nahi hai, 24 microhenry hai. Please check whether I have done some mistake or not. I think I have done some mistake. Calculation mistake. 24 V in and V out 48. Okay, this is 120. Okay, 48. So since it is a boost converter, so 1 over 1 minus D. So D will become half. That is correct. D is half. Okay, and the resistance value, power is 120 watt. So I naught into 48 is 120. P out is 120, na? Okay, so it will be 120 divided by 48. 120 divided by 48 is the output current. So 12 10 पे गया, 12 चौक 48, ये 2.5 ampere. This is correct. I naught is 2.5. Multiply by 2, this is the 5 ampere. Okay, so this comes out to be 5, this is 2.5. Average inductor current is 2.5. Okay, because average current from this side is 5 ampere and average current going on this side is 2.5 ampere. So the inductor average current is, what is the inductor average current? I think I have done mistake here. Average current through the inductor is 7.5. It should be 7.5. Why it is 7.5? Can you tell me? Why it is 7.5? It should be 7.5. Because the average inductor current will be the average of this source current and average of this current. So it has to be 7.5 ampere. Average inductor current has to be 7.5. Now we know that average inductor current is 7.5 and IL min is 0. And what is IL min? IL minus delta IL by 2. It has to be 0. So delta IL by 2 is 2 times of IL, 2 times of 7.5. So it has to be 15 ampere. Delta IL is 15. IL max minus IL min, it has to be 15. So this is delta IL. So delta IL is this and it has to be 15. So in the denominator I have to write 15 here. Okay, I have to write 15, and if you solve it you will get let's solve this problem. This is 0.5, no? 0.5. This is 15. So what you can do is you can write 2.5 divide by 2.4 divided by. Only thing is calculation. Everything is otherwise simple. Okay? So it will be 24 into 0.5. 24 into 0.5 is 12. Okay. Please check this whether I have done it correctly or not. This is 15. D is half. L we need to calculate. F is given as 50 kilohertz. So 50 kilohertz is written here. Input voltage is 24. Okay. Average current is 7.5 is correct. Wait. Everything is fine. Double of that is 15. Delta L is 15. IL max minus IL min is 1 by L. I think everything is perfect. I need to calculate this value. Okay, so it will be 24 into 5 divided by 15 into 500. Okay, because what I have done is I have removed this decimal place. Okay, so this is 3 8. Okay, so 8 by 500, 8 by 500 millihenry. Okay, so I can write it like this. Again there is some mistake. Okay, let's try to solve it from the scratch. Well, let's try to solve it from the starting. Okay, let me remove this. Let me erase. Wait. Sometime it happens. Okay, let's try to solve the problem. Okay, so the problem says we have a DC-DC boost converter. Okay, the duty ratio is controlled. The duty ratio is controlled to regulate the output voltage to 48 volt. It means the output voltage is kept constant at 48 volt, and it is a boost converter. Boost converter. Okay, the input DC voltage is 24 volt. V in is 24 volt. Okay ji. And the output power is 120 watt, right? Frequency is 50 kilohertz. Frequency is given as 50 kilohertz. Assuming all components are very large and output will, the converter operate at the boundary between continuous and discontinuous conduction. It means just continuous. Okay, inductor current is just continuous. The value of the boost inductor in microhenry. Okay, we need to calculate the value of the boost inductor in microhenry. So what I can do is, let's first draw the circuit. Okay, this is the boost converter we have. Please check the diagram of the boost converter, because previously also we have solved the boost. This is the boost converter. The circuit I have used is wrong. Excuse me guys. That's why mistake happened. This is the boost converter. Excuse me. So you have to remember the circuit of the boost converter. Okay, so we have this boost converter, and the input voltage is 24, output voltage is given as 48. All right. Okay, now we know that output upon input is 1 over 1 minus D, duty ratio. Okay, from here you can say that duty ratio comes out to be half, and this is also IS upon I0. Let's first calculate the value of I0. I0 comes out to be 2.5 ampere. Why? Because 2.5 into 48 is 120. If you know the value of I0, okay, then IS will be double of that, 5 ampere. Okay, this current is 5 ampere, and this is the average inductor current, because the source current and the inductor current remains the same. It means we know the average current flowing through the inductor. Okay, now since the conduction is just continuous, so IL min has to be 0. Now how to calculate IL min? IL min is equal to average inductor current minus delta IL by 2, and it has to be 0. So from here, delta IL by 2 has to be equal to IL. So delta IL comes out to be 2 times of IL. Okay, average inductor current times 2. This is the average inductor current. Sorry, it is the delta IL. Average inductor current is 5 ampere. Multiply by 2 will become 10. So delta IL comes out to be 10 ampere. Delta IL is 10 ampere. Till this point there is no problem. Now what is delta IL? Delta IL during this on period, during this DT time, you can see that the switch is on, inductor voltage is at 24 level. Okay, 24 volt. So if I calculate this change in current, inductor current, delta IL, then delta IL will be equal to 1 by L integration 24 dt 0 to dt. Okay, so this comes out to be 24 d t upon L. So t I can write it 1 by f. Okay, and this has to be equal to 10. Delta IL has to be 10. Now what about this? Oh, so this is 24 d into t I can write 1 by f into L. This has to be 10. So L is equal to 24 into half divide by 10 into f. F is 50 kilohertz. 50 kilohertz. The kilo will convert into millihenry. Okay, now you can see that this is 12 upon 500 millihenry. 12 upon 500 millihenry. So it comes out to be 24 microfarad. 24 microfarad. So the answer is 24 microfarad. So this was a simple problem. Only mistake we were doing was the diagram of the boost converter. Okay, that was the mistake. So I hope you understood it. Let's come to the next problem, and the next problem is question number 25. So try to solve this question. Question number 25. Okay, you can see on your screen. Let me erase all these calculations which I have done. Okay, now let's try to solve question number 25. Do it, guys. It's a 2-mark problem. Do it. Question number 25. So I'm giving you again 2 to 3 minutes for this problem. Solve it. 2 to 3 minutes for this problem. Solve it, everyone. जल्दी करो, do it fast everyone. Okay, let's solve it. Let's try to solve this problem. So we have a DC-DC converter shown in the figure. The switch Q is switched at a frequency of 10 kilohertz and the duty ratio is 0.6. Okay, all components of the circuit are ideal and the initial current in the inductor is 0. The energy stored in the inductor at the end of 10 complete cycles, switching cycles. Okay, this is the inductor. So let's say that this is VLT. Let's draw the voltage VLT. During the on period, if the switch is on, the current will flow like this. Okay, so this will be the circuit in which the current will flow during the on period. Okay, the current will flow like this, it will go like this. Okay, inductor voltage is 50 volt during on period. Inductor voltage is on period and the on period is 0.60 dt time. Okay, for 0.60 the voltage is positive. Now if you turn off the switch, this current will flow like this. Okay, and the inductor voltage is minus 50. Inductor voltage is minus 50 up to this time t. Okay, and then again the cycle will repeat. Okay, so this will be the voltage across inductor. Now you can see that average voltage across inductor is not 0. VLT average is positive. So what will happen to the current? So current will start from 0, will go like this and then come down like this and then again will go like this. It means in every cycle it has gained some value. How much current, how much value it has gained? In the first 0.60 time, let's calculate ILT. So IL peak, let's calculate. Initial current is 0 plus 1 by L, L is 10 millihenry, integration 0 to 0.60 and the voltage across inductor is 50 dt. Okay, so it will become 50 into 0.6 t. T is 1 by f, 10 raised to the power 4 hertz. 10 kilohertz means 10 raised to the power 4 hertz. Okay, so 50 into 0.6, 1 by f, and in the denominator you have 10 raised to the power minus 2 as well. Okay, this is 10 raised to the power minus 2. So this is IL peak, this value. Now how much you'll get, how much this value you will get? So it is 10 raised to the power 2. Okay, denominator is 10 raised to the power 2. So 0.6 by 2, it will be 0.3 ampere. So this value is 0.3 ampere. Okay, now during this interval, what will be this value? So initial value is 0.3 plus 1 by L. 1 by L is 10 raised to the power minus 10, 10 raised to the power minus 2. 1 by L. Okay, integration volt minus 50 dt, and how much time we have? 0, let's call this time as 0 to 0.4 t. So it will be minus 50 upon 10 raised to the power minus 2 into 0.4 t. T is 1 by f, f is 10 raised to the power 4. Okay, now you can see this is 100 and this is 2, so it will become minus 0.2. This is minus 0.2. 0.3 is the initial value, minus 0.2, 0.3 minus 0.2 is 0.1. Okay, so this value is 0.1 ampere. It means after completion of one cycle, the inductor has gained a value of 0.1 ampere. Okay. Now at the end of 10 complete cycle, inductor has gained a current of 1 ampere. 0.1 into 10. After 10 cycle, at the completion of the 10th cycle, it will gain 1 ampere, because in one cycle it is gaining 0.1 ampere. So in 10 cycle, it will gain 1 ampere. Okay. So how much energy will be stored? Half Li square. Okay. L is 10 milliampere, 10 millihenry, and I is 1. So it will become 5 millijoule. It will become 5 millijoule. Okay. Energy in the inductor in millijoule is asked. So answer is 5. Let me see the answer. Which question is this? 25. 5 is the correct answer. Okay, let's move to the next question. Question number 26. Question number 26 is on your screen. It is 1 mark question. I'm giving you time of 1 to 2 minutes. Okay, try to solve this question, everyone. सर सिग्नल की क्लास होगी क्या? है ना, बता दीजिए. साहिल सोनी आज पता नहीं भाई, मैं बता दूंगा थोड़ी देर में. Okay, tell me guys, what is the correct answer of this question? Question number 26. I'm giving you 2 to 3 minutes. 1 to 2 minutes. Do it fast. Do it fast, everyone. So guys, you ready? Okay, let's see. Power electron converter shown in the figure has single pole double throw switch. The pole P of the switch is connected alternatively to throw A. The converter is shown as, okay, which converter is this? It's a step down converter, or a half wave rectifier, or a step up chopper, or a full wave rectifier. So what we can do is we can calculate the voltage of this with respect to this. When the pole is at this point A, the voltage at this level, at this, I mean the voltage between these 2 points will be V in, okay, and if the pole is at this point, the voltage is 0, okay, this is the voltage we will get, okay. Now we know that because of this voltage, current will flow in this circuit, and under steady state, because the steady state has to reach, under steady state this current will be periodic and the average voltage across inductor will be 0. So whatever average this voltage has, whatever average this voltage has, let's call it Vs, whatever average this voltage has, the same average voltage will appear here. Why? Because the average voltage across inductor has to 0. Now what is the average voltage of this Vs? Average voltage is this, and it is less than input voltage. So it's a step down chopper, it's a buck converter. Okay, I hope you understood it. ठीक है, पूरा इसमें PYQ डिस्कस किया है आशीष, इन्वर्टर डिस्कस हो गया, अभी बक बूस्ट कन्वर्टर चल रहा है. ठीक है, so guys, let's move to the next question. Okay, so next question is asked in GATE 2026. Okay, come back 26. Wait. Okay, so we have solved up to 26, 2010. Let's move to the next question, next page. So in the next page we can start from question number 17 onward. Okay, let's solve these questions. Question number 17 and 18, we have to solve these two questions, and I am giving you 2 to 3 minutes for this question and 3 to 4 minutes for this question. Okay, try to solve it. You have 2 to 3 minutes for this question and 3 to 4 minutes for this question. Solve it, everyone. Do it fast. Do it fast. Do it fast, everyone. Okay, done. It's 17, 16 volt. When the switch of peak will appear. Okay, let's see. Question number 17. A buck boost DC-DC converter shown in the figure below is used to convert 24 volt. Wait. Okay. Let's solve this problem now. A buck boost converter shown in the figure convert 24 volt battery to 36 DC voltage. Okay. So 24 volt to 36 volt. Okay. To feed a load of 72 volt. To feed a load of 72 volt. Okay. So it is 72 volt load. Okay. Feed a load of 72 volt. It is operating at 20 kilohertz. Okay. With an inductor of 2 millihenry and output capacitor of 1000 microfarad. This is 1000 microfarad. All devices are considered to be ideal. The peak voltage across the solid state device. Across this device, we need to calculate the peak voltage. Okay. So I think it's very simple. When the switch is on, the voltage across this device is 24 because this is sort. Wait. Okay. When the switch is on, the voltage across this device is 0. Okay. When the switch is on, voltage across this device is 0. When the switch is off, during the off period, let's say this is grounded, this voltage is 24 volt, and when this is off, the diode will conduct. It will be sorted. And this 36 volt, since the lower point is 0 volt, this upper point will be at minus 36 volt. Okay. So this is 24, this is minus 36. So the voltage across this device is 24 minus or minus 36. Okay. So it will become 60 volt. So the answer is 60 volt. Okay. So the answer is 60 volt. Let's come to the next question. Question number 18. In question number 18, it's a DC-DC boost converter. It is used to boost 360 volt to 400 volt like this. Okay. Power is 4 kilowatt. Okay. All devices are ideal. Consider continuous inductor current. Okay. Continuous conduction is there. RMS current in solid state switch. RMS current through this switch we need to calculate. Now how to calculate the RMS current? RMS current, it's not easy to calculate, but let's try to solve the problem. We know that since the conduction is continuous, output voltage upon input is 360, output voltage upon input is equal to 1 over 1 minus D. It's a boost converter, na? So let's cut it. So you can say that 1 minus D is equal to 0.9, D is equal to 0.1. Okay. D is equal to 0.1. Up to this point, I think there should not be any problem. Okay. Now the same ratio is IS upon I0. Okay. It means IS will be equal to I0 divided by 1 minus D. What is I0? I0 you can calculate from this power. 4 kilowatt divided by 400. So this current, I0 current is equal to 10 ampere. Okay. I0 is 10 ampere. So I can put it here. I0 I can put it here. So IS will be 10 divided by 0.9. 100 upon 9 ampere is the average current through this source. The source average current is 100 by 9, and the inductor average current is also 100 by 9 because the inductor current and the source current is same. Okay. But we want to calculate RMS current through the switch. Okay. Let's draw the inductor current, inductor voltage first. We know that when the switch is on, the inductor voltage is 360. During the on period, inductor voltage is 360. During the off period, inductor voltage is 360 minus 400, so it will be minus 40. Minus 40 during the off period. Okay, during on period it is 360 and during off period it is minus 40, right? Okay, and the inductor current will go like this. Inductor current will go like this. It is a continuous conduction, so it will go like this. Okay, this is the inductor current. Current will be periodic. Now if you want to calculate the current through the switch, then the current through the switch will only flow when the switch is on. It means during on period. So if I draw the current through the switch ISW, then that will be like this, and then 0, and then again during on period it will be like this. Okay, this is the switch current. Now we need to find the RMS value of this current. RMS value of this switch current. How to calculate the RMS value of this switch current? For that we need to find this ILmin and this ILmax. ILmin and ILmax we need to find. We know the average inductor current. What is the average inductor current? Average inductor current is average source current, which is 100 by 9. 100 by 9 is the average inductor current, or you can say average source current. What is this ILmax and ILmin? How to calculate that? Let's first calculate delta IL. Delta IL is 1 by L integration 0 to dt. D is 0.1, so 0 to dt. Voltage across inductor is 360. Okay, this is delta IL. Let's calculate this. So delta IL is, let me write it here, 360 into 0.1, T is F, 1 by F, okay, 0.1 into 10 to the power minus 2, right? And F is given as, frequency is not mentioned. Okay, if frequency is not mentioned, we cannot calculate delta IL. Okay, so how to solve this problem? There is no way we can solve this problem. The only one way is there, and that way is whatever this average current through the inductor is flowing, you have to assume that the inductor current is constant. Otherwise there is no other way, because we cannot calculate this change. Once the change is known to us, we can calculate this IL max and IL min, and then we can calculate the equation of this current, and then easily we can calculate the RMS value. But the problem is we do not know the frequency, switching frequency. If we do not know the switching frequency, we cannot calculate delta IL. Okay, and if delta IL is unknown to us, we cannot calculate the RMS value. So RMS value of this current is unknown to us. But what we can do is, we can assume that this current is constant. Inductor current is constant. We assume that the inductor current is constant at 10 by 100. And when the switch is on, during the on period, whatever the inductor current, the same current will flow through the switch. It means what we can do is, we can draw the inductor current, the switch current during this on period. Whatever the inductor current is, the same current will flow through the switch, and during off the current is 0, and again during on this is 10 by 9. Okay, so we can show the inductor the switch current like this, and now we can calculate the RMS value of this, and the answer given is according to this condition. But that is wrong. We cannot do that. Okay, this is wrong. We need to find delta, the frequency should be given, switching frequency should be given. So this question technically should be marks 2 all, but at that time nobody claimed for that question. So there is only one way to solve this problem. You have to assume that this current has to be constant, then only you will be able to solve it. Okay, I think now you can solve this problem, question 18. Let's move to question number 19. Let's move to question 19. Okay. Now question 19, you can see that the input VDC of a buck boost converter, we have a buck boost converter, okay, we have a buck boost converter, and the diagram is given here, okay. The input voltage of buck boost converter varies from 32 to 72 volt, okay, it varies from 32 to 72 volt. Assume all the components are ideal, inductor current is continuous, okay, conduction is continuous, and output voltage is ripple free, it means output voltage is constant. The range of the duty ratio D, the range of D we need to find, for which the magnitude of steady state output voltage remain at 48 volt. We want that this voltage should remain at 48 volt, and input varies from 32 to 72, conduction is continuous. We need to find the range of D. It's an easy peasy problem, very easy. I'm giving you 2 minutes, solve it. 2 minutes to solve this problem. Do it, guys, do it fast. Do it fast. Do it fast, everyone. So what you need to do is, first assume that this voltage is 32 and this voltage remain at 48 volt, and since it is a buck boost converter, so V out upon V in, VDC, is equal to D over 1 minus D. For continuous conduction, this formula is applicable. So in the first case, you take output voltage at 48 volt and input at 32, D over 1 minus D, okay. So from here you can calculate 3 minus 3D equal to 2D. So D comes out to be 3 by 5, 0.6, okay. So in the first case, if you take this 32 and this as 48, then D has to be 3 by 5, okay. In the second case, take it as 72, so 48 by 72, output by input, equal to D over 1 minus D, okay. Now you can see that this is 2 by 3, okay. So D over 1 minus D is 2 by 3. Now you can say that 3D equal to 2 minus 2D. So D come out to be 2 by 5, 0.4. It means D has to be greater than this and less than 3 by 5. Greater than 2 by 5, less than 3 by 5. Answer is Agra. Easy peasy. Let's move to the next question. Question number 20. It's a 2-mark question and I am giving you 2 to 4 minutes for this, okay. Try to solve this problem, everyone. Question number 20. Question number 20. Okay, try to solve this problem. Question 20. Do it fast. Do it fast, everyone. Have you solved it? Question number 20. Let's see. The circuit shown, all the elements are ideal and the switch S is operated at 10 kilohertz. Okay. Operated at 10 kilohertz and 60% duty ratio. D is 0.6. Okay. Frequency is 10 kilohertz. Okay. 2 minutes. Okay, you want me to wait? Okay, do it fast then. Do it fast. It was asked in 2017. 2 marks. TMs. Okay, let's check. So in the problem, frequency is given as 10 kilohertz and duty ratio is 60%. It means D is 0.6, frequency is 10 kilohertz. The capacity is large enough so that the ripple across it negligible and steady state acquires a voltage. 75 volt is across this capacitor and this resistor. Okay, so this is the output voltage and it's a buck boost converter, we know that. Input voltage is 50 volt. The peak current in amperes drawn from 50 volt DC source. We need to calculate what will the peak current through this source. Okay, so what I can do is, let's first assume that the conduction is continuous, but we do not know whether the conduction is continuous or discontinuous. So we are assuming that conduction is continuous. conduction is continuous. Okay, but we have to re-verify, recheck it. Okay, so if the conduction is continuous, then the output voltage upon input voltage is equal to d over 1 minus d. Okay, so from here you can see that 3 minus 3d is equal to 2d. So 5d is equal to 3, d is equal to 0.6. Okay, duty ratio comes out to be 0.6. Fine. Okay, perfect. Now we know that if this is 75, how much current will flow from here? Wait. Okay, now it's visible. So now tell me, if this is 75, how much current will flow from here? 75 upon 5. 75 upon 5 is 15 ampere. Okay, 15 ampere will flow like this. This is the average current. So this has to be equal, this ratio has to be equal to d over 1 minus d has to be equal to is over I0. Okay, and d is 0.6, so 0.6 over 0.4 is equal to is over I0 is 15. Okay, this is 3 by 2, so is is equal to 15 into 3 by 2, right? This is 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 45 by 2 ampere, right? So the average current from this source has to be 45 by 2 ampere. Is it correct, guys? Up to this point, is there any problem? Please check. D over 1 minus d is equal to is over I0. So d is, what is d value? D comes out to be 0.6. So 0.6 over 0.4 is equal to this. So this is 3 by 2. 15 into 3 by 2. So 15 into 3 by 2 is 45 by 2. So this current is 45 by 2, average current. Okay, average current is 45 by 2. Now let's look at the inductor, because we have to check whether the conduction is continuous or discontinuous. This is the average current, remember that. Now let's draw inductor voltage VLT. When the switch is on, inductor voltage is at 50 volt, and when switch is off, inductor voltage is minus 75. Okay, this is minus 75. This is dt and this is t. Okay, and I'm assuming that the conduction is continuous. It means the inductor current will go like this. Okay, what about the inductor average current? What about the inductor average current? We know that inductor average current will be the sum of these two currents. Okay, the sum of these two currents. 45 by 2, which is 22.5 plus 15, 37.5. So the average value of this current is 37.5. Now if I can calculate this delta IL, then I can check whether the conduction is continuous or discontinuous. So delta IL is equal to 1 by L, 1 by 0.6 millihenry. Okay, 1 by L 0 to dt into this voltage 50. Okay, so this comes out to be 10 to the power 3 upon 0.6 into 50 into d. D is 0.6 into t. T is 1 by f. F is 10 kilohertz. 10 into 10 to the power 3. This is cancelled. Okay, this is again cancelled. This is cancelled. So delta IL is 5. Delta IL comes out to be 5. Now what is this IL min? IL min is 50 minus delta IL by 2. Not 50, 37.5 minus. 37.5 minus delta IL by 2. Delta IL by 2 is 2.5. So IL min is positive. If IL min is positive, conduction is continuous. It means all the calculation we have done is correct. Fine. Now, what is this IL peak? IL peak is equal to 37.5 plus delta IL by 2. 37.5 is the average value plus delta IL by 2. How much delta IL is? Delta IL is 5. 5 by 2 is 2.5. So 37.5 plus 2.5 is 40 ampere. IL peak is 40 ampere. And we know that whatever peak current through this inductor will go, the same peak current will come from the source, because whenever the switch is on, during that on condition, the inductor current and the source current will be same. So if IL peak is 40 ampere, then the source peak will also be 40 ampere. Okay, because this is during on period. During on period, current is flowing like this, and during on period, inductor current and the source current are same. So the maximum value is 40 ampere. It means the source current peak value is also 40 ampere. Answer is 40. Okay, 40 is the correct answer for question number 20. Okay guys, so these were the questions, and I think we should stop here. Okay, because the time is over now. So I have solved almost 25 questions from this buck boost converter, and almost last 20 years questions from inverter. Okay, and I hope that you got some good analysis, and you got the solution for those questions. Okay guys, so that's all for today's session. If you have any kind of doubt, please ask. If you have any problem, you can ask me now, because today's session is over now. The next class will be on tomorrow, and tomorrow's class will be on instrumentation. Okay, we'll solve the PYQs of instrumentation. Okay everyone. No, power electronic sessions are over, because this was the PYQ session. Till GATE 2026, no power electronic session will be there. Next session will be of instrumentation. Okay, tomorrow I have one more session in under PYQ, and that session will be of instrumentation. Okay, measurement and instrumentation. So that's all for today's session guys. I hope you enjoyed. So see you tomorrow. Take care.